I think it's about time to begin the session. We have probably about 1 minute till 10 o'clock to start the morning session. I would like to say it's my privilege to chair this morning session in honor of Academician Drensky. And our first speaker this morning is Francesca Benanti from the University of Palermo. Her talk will be on the asymptotics of Stargate Capelli identities. And I think you can see her screen, and from now she can take over for the next 25 minutes. Francesca?
Yes, it's okay. You can see? Okay. Okay, good morning, everyone. And before starting, I would like to thank Vesselin to give me the possibility to participate in this conference. And also, I would like to thank Vesselin for warm welcome during my PhD study periods in Sofia for his very important teachings. Thank you very much, Vesselin, for all. So, in this talk, I'm going to present my recently result about Stargraded Capelli polynomials. These results are in joint paper with Angela Valenti. And at the beginning, I'll survey some of the results on Capelli polynomial. And at the end, I present this recently result. Okay, let F be a field of characteristic 0 and A in associative algebra over F, we denote by f of x the free associative algebra, and by id of A, the set of all identities of A. Also, we denote by var the variety of algebra having the T ideals of the set of identity of A as corresponding to ideal. And in a very important class of T ideal is the class of verbally prime T ideal. This is the definition. Also, we recall that a variety is called verbally prime, so the corresponding T ideal is verbally prime. And also, we say that A is verbally prime. This T ideal was introduced by Kemmer in his solution of the spec problem, and as basic block for the study of generic variety. Also from the Kemmer's theory, it turns out that a variety is verbally prime if and only if A is one of the following algebras. And now it's a very important problem in the PI theory to describe the verbal prime T ideals. It's well known that in characteristic 0, every T ideal is completely determined by its multilinear polynomials. So to study a generic T ideal, we can use the end codimension of A. And Vn is the space of multilinear polynomials of degree n. It's clear that if A is a PI algebra, then the encodimension is less than factorial. And Regev proved that the encodimension is exponential bounded. According to several examples provided by Berel and Regev, Amzur conjectured that the exponential growth of the codimension sequence should be an integer. Giambruno and Zaitsev confirmed this conjecture, and they proved that if A is a PI algebra, then this limit exists. It is a non-negative integer, and it's called the PI exponent of A. The following for the verbal prime algebras, we have this result for the exponent, and the asymptotics of the codimension have been studied in all three cases, but only in the first case the constant alpha is known. There was found some relation between the T ideals, the verbal prime T ideals, and the T ideals generated by Capelli polynomial. We recall the definition of Capelli polynomial. This polynomial were introduced first by Razmistrov in his construction of central polynomial for matrix algebras. And also we recall the definition of Amzur's Capelli type polynomials. And we note that for L equal to 0, the Amzur-Capelli type polynomial is a Capelli polynomial. So we can say that Amzur's Capelli type polynomial generalize Capelli polynomial. Also because it's well known that Capelli polynomial characterize algebra, associative algebras having the co-character in a given strip. Instead, Amzur's Capelli type polynomial characterize algebras, associative algebras having co-character in a given hook. It's well known the following relation between the exponent of the verbal prime algebras and the T ideal generated by Capelli polynomial and the T ideals generated by Amzur's Capelli type polynomials. And Giambruno and Zaitsev proved also that the codimension of the verbal prime the verbal prime algebra MK of F is asymptotically equal to the codimension of the T ideal generated by Capelli polynomial of degree k squared plus 1. In a joint paper with Irina Sviridova, we obtain analogous results for the other verbal prime algebras. Okay, now I'm going to relate analogous results on superalgebras and graded Capelli polynomial. So, if we write X as a disjoint union of two countable sets, the free associative algebra has a natural structure of free superalgebra with the following grading. F up 0 is the subspace generated by monomials of even degree with respect to Z, and F up 1 is the subspace generated by the monomials of degree with respect to Z. Below, we recall the definition of superalgebra. And as in the ordinary case, we can consider graded identity or super identity for superalgebra A. And also we can consider the set of all graded identity of A with denoted by this symbol, id sup of A. And by sup var, we denote the supervariety of superalgebras having the elements of this T2 ideal as graded identity. And from the Kemmer theory, it turned out that superalgebras are very important in the study of associative variety. In fact, Kemmer proved that any associative variety is generated by the Grassmann envelope of a suitable finite dimensional superalgebra. Also, Kemmer proved that an associative variety is a prime variety if and only if it is generated by the Grassmann envelope of a finite dimensional simple superalgebra. Kemmer also proved that a simple finite dimensional superalgebra is isomorphic to one of the following algebra. It's very important that the following problem to describe the T2 ideals of graded identity of the simple finite dimensional superalgebras. And as in characteristic 0, we can consider to study these T2 ideals as in characteristic 0, we can consider the end supercodimension of A. This is the dimension of the following quotient. Vn sup is the space of multilinear polynomials of degree n in variables y1, z1, yn, zn homogeneous. Okay, Giambruno and Regev proved that the supercodimensions is exponentially bounded if and only if A satisfies an ordinary polynomial identity. And in a joint paper with Giambruno and Pitone, it was proved that in the case of A is a finitely generated superalgebra satisfying a polynomial identity, then exists the super exponent, this limit, and it is a non-negative integer. Also, we obtain the following qualities for the finite dimensional simple superalgebras. In general, it was proved by Aljadeff and Giambruno that if A is an algebra graded by a finite group satisfying an ordinary polynomial identity, then the G exponent of A exists and is a non-negative integer. The partial results were obtained by Di Vincenzo and Nardozza. In the case of G is a group of a prime order, Giambruno and Lamattina, in the case of G a finite abelian group, Aljadeff, Giambruno and Lamattina, if A is a finitely generated algebra and G a finite abelian group. So, what about the codimension, the supercodimension? Karasik and Spiegelman proved that if G is a finite group, then the G graded codimension sequence of a finite dimensional G simple algebra A is the following. Alpha is some positive real number and A epsilon denotes the identity component of A. In the special case where A is the algebra of matrices with an arbitrary elementary G grading, the constant alpha was explicitly calculated. Then in the case of G is a group of order 2, we obtain the asymptotic value of the supercodimensions. Okay, now inspired to the ordinary case, we can consider the graded Capelli polynomial. This is the following polynomial in the homogeneous variables T1 and Tm. In particular, this is graded Capelli polynomial in alternating variables of homogeneous degree 0, and this is the n-graded Capelli polynomial in alternating variables of homogeneous degree 1. It was proved that the following equalities for the super exponent of the finite dimensional simple superalgebra and the T2 ideal generated by graded Capelli polynomials. Also, the asymptotic inequality between the super exponent of the finite dimensional simple superalgebra and the T2 ideal generated by the graded Capelli polynomial has been found. Okay, now I'm going to talk about similar results on algebra with involution. We consider the free associative algebra over F with involution star, with Y is the set of symmetric variables, and Z is the set of skew variables. Also, if let A be an algebra with involution, we denote by id star the set of all star identity of A, and by var star of A the variety corresponding to this T star ideal. And it's well known that in the case of F is an algebraically closed field of characteristic 0, all star simple finite dimensional algebra are the following one. matrix algebra with the transpose involution, matrix algebra with the simplex involution, and the direct sum of the algebra of K by K matrices and the opposite algebra with the exchange involution. So now we have also the same problem to describe the T-star ideas of the star polynomial identities of star simple finite dimensional algebra. And also in this case, we can consider the end star codimensions in characteristic 0. And we know the following result of Giambruno RGF. If A satisfies a non-trivial star polynomial identity, then the star codimension is exponential bounded. And also, Bakhturin, Giambruno, and Zaitsev found an explicit exponential bound for the star codimensions. The following the asymptotic behavior of the star codimensions of the star simple finite dimensional algebra has been determined. Gamma is the Euler's function, also in this case. And about exponent, Giambruno and Zaitsev proved that if a finite dimensional algebra with evolution, then the star exponent exists. And Giambruno, Pulsino-Milies, and Valenti extend this result for any algebra with evolution A. It's well known that the star exponent of the finite dimensional star simple algebra is equal to the dimension of the algebra. Now, we consider also, in the case with involution, the star Capelli polynomial. This is the star Capelli polynomial alternating in symmetric variables y1, ym, and this is the m star Capelli polynomial in skew variables z1, zm. x1, xm minus 1 are arbitrary variables. In a joint paper with Angela Valenti, it was proved the following equality between the star exponent of the finite dimensional star algebras and the star exponent of the T-star ideal generated by star Capelli polynomials. Also, in this paper, we found the asymptotical equality with the star codimension of star finite dimensional algebra simple and the star T ideal generated by Capelli polynomial with involution. Now, at the end, I'm going to present recently result obtained in a joint paper with Angela Valenti. In this case, we consider the graded involution. Now, let a field of characteristic 0, we consider the free star superalgebra over F with graded involution star. Y plus are symmetric variables of even degree, Y minus are skew variables of even degree, Z plus are symmetric variables of odd degree, and finally Z minus are skew variables of odd degree. Allora, we recall that given a superalgebra A endowed with an involution star, we say that star is a graded involution if it preserves the homogeneous components of A. Also, a superalgebra endowed with a graded involution is called star superalgebra. Let A be a star superalgebra. The polynomial F is a graded polynomial identity for A if F is equal to 0 for all substitutions of elements of the homogeneous component of A. We denote with this symbol the set of all star-graded polynomial identity of A. This is a two-side ideal invariant under all endomorphisms of the free star superalgebra that preserve the superstructure and commute with the graded involution star. We denote by var star Z2 of A the variety corresponding to this T ideal. From a paper of Giambruno, Dos Santos, and Vieira, we have the following result. The only finite dimensional simple star superalgebra are the following. Diamond denotes the transpose or symplectic involution. Exchange is the exchange involution. Okay. And problem. To describe the T2 star ideal of the star-graded polynomial identity of finite dimensional simple star superalgebra. We can consider also in this case, to study this problem, the n star-graded codimensions of star superalgebra. And Giambruno, Dos Santos, Vieira proved that if A is a PI algebra, then the sequence of the star super codimensions is exponential bounded. By Gordienko proved that if A is a finite dimensional PI algebra, then exists the star-graded exponent, and it is a non-negative integer. By result of Giambruno, Iocco, e Lamattina, the existence of the star-graded exponent is extended to any finitely generated PI star superalgebra. By the result, by the paper, from the paper of Gordienko, we obtain the star super exponent of a finite dimensional simple star superalgebra. And now an open problem is that of determining the asymptotic value of the sequence of the star codimensions of the star super codimensions of a simple star superalgebra. Maybe to study this problem can be useful to know the Capelli polynomial. So we define the following star-graded Capelli polynomial. This is the star-graded Capelli polynomial alternating in symmetric variable of homogeneous degree 0. This is star-graded Capelli polynomial alternating in skew variables of degrees 0, and this is star-graded Capelli polynomial alternating in symmetric variables of degree 1 at the end. This is the star-graded Capelli polynomial alternating in skew variables of degree 1. So we denote by gamma del T by gamma, the T ideal generated by the T2 star ideal generated by star-graded Capelli polynomial. And in recent paper with Angela Valenti, we proved that if A is a finite dimensional simple star superalgebra, then the star super exponent of A is equal to the star super exponent of the T ideal generated by star-graded Capelli polynomials. And the main result of our paper is the following theorem. For suitable natural numbers, there exists a finite dimensional simple star superalgebra A such that we have the following equality. D is a finite dimensional star superalgebra such that the star exponent of D is less m plus L. In particular, we have the following algebra: the star simple superalgebras, finite dimensional. As a corollary, we obtain the asymptotic value of the asymptotic value of the star super codimension of finite dimensional star superalgebra is equal to the star codimension of star super codimension of the T ideal generated by Stargardt-Capelli polynomial. Maybe this result can help us to give a solution to the open problem. Okay, that's all. I finish. Thank you. Thank you.
Thank you, Francesca. You finished right on time, so we have a minute for questions. It seems like there are no questions. Thank you again. Our next speaker is Maja Stoyanova from Sofia University. She will talk on orthogonal arrays and their distance distributions. Maja, you take over from now on.
Thank you. This is a joint work with Silvia Bumova and Peter Voivolenko. Silvia Bumova work and Faculty of Mathematics and Informatics at Sofia University, and also at Institute of Mathematics and Informatics, Bulgarian Academy of Sciences. And Peter Voivolenko is now Director of Institute of Mathematics and Informatics, Bulgarian Academy of Sciences. So this is the outline of our talk. We present the orthogonal arrays, some general problems for investigations, some basic properties. Our investigation based on the investigate distant distribution of the orthogonal arrays, and our results in this talk present some upper bounds for the covering radius and for the minimum distance via distant distributions. So, in 1940, Rao introduced certain combinatorial arrangement named orthogonal arrays. They play important roles in statistics, computer science, and cryptography. Orthogonal arrays are related to combinatorics, finite field geometry, error correcting codes, and so on. Although there are still many unsolved problems, let H be an alphabet of Q letters, and H power Q power n be the n-dimensional Hamming space over this alphabet of Q letters with the usual distance between 2 points x and y. That is the number of places in which they differ. So an orthogonal arrays of strength T and index lambda in n-dimensional Hamming space consists of the rows of m n times n matrix T, with the property that every m times T submatrix of C contains all order T tuples of the Hamming space, each one exactly lambda times as rows. We denote such orthogonal array C by MNQT orthogonal array. Definition 1 allows repeating rows, but we will usually assume that the initial orthogonal arrays are simple, that is, they do not possess repeating vectors, but it will allow repetition in their related orthogonal arrays obtained by deleting columns of the originals. The important parameters of the orthogonal arrays, the cardinality M, that is the number of rows, the dimension, that is the number of columns, the levels, that is the number of symbols of alphabets, and strength T. It's clear that every MNQT orthogonal array is also MNQT prime for every positive integer T prime less than T. The index lambda, for index lambda, there is the following relation. The number of points, that is the number of rows of the matrix, is equal to lambda times Q power T. It was proved by Delsart that if C is code of n-dimensional Hamming space, that the strength of C is related to its dual distance by the following way. So here we present a very easily example to explain this construction orthogonal or combinatorial construction orthogonal array. This is the shortened Hamming code of length 5. Is an 8522 orthogonal arrays. It's easy to check that every 2 columns defines a submatrix with all 8 possible distinct rows. So the index of this orthogonal array is 2. We need to use some basic properties of orthogonal arrays, and the next 3 slides we present these basic properties. So if orthogonal array with parameters m and qt, the following properties hold. First we know the connections between index and cardinality. Second and third properties is important for our investigation. A permutation of the symbols levels of any factors in an orthogonal array results in orthogonal array with the same parameters. And a permutation of the runs or factors, that is the columns n, in again orthogonal arrays with the same parameters. Any m times k subarray of orthogonal m and qt arrays is an orthogonal m k q t prime arrays where t prime is minimum of t and k. If A is an orthogonal m and qt array, and here A1 itself is an M1 and QT1, and A2 is an orthogonal array M minus M1 and QT2 with T2 greater than equals to minimum T and T1. So the next property is present that existence of orthogonal array M and Qt implies existence of Q orthogonal arrays with parameters M over Q, N minus 1, Qt minus 1, that is orthogonal arrays A0, N1, and Q minus 1 of the present constructions. So the opposite property is that if AI is orthogonal array with Mi points and Q and Ti strength, then we can obtain orthogonal arrays with parameters M, Q, T by the following constructions with cardinality M, the sum of cardinality of the original arrays, and strength T with some T greater than equals to minimum of the strength of the original arrays. Further, when M is equal to Q, the number of symbols of alphabet, and each orthogonal arrays is M and Qt, after appending a 0 to each rows of N1, a 1 to each rows of A2, and so on, we obtain an orthogonal arrays with cardinality Qm, N plus 1, Qt. In particular, existence of the M, N minus 1, Qt minus 1 orthogonal arrays imply existence of Qm and Qt orthogonal arrays. So we said that two orthogonal arrays be isomorphic if one can be obtained from the other by a sequence of permutation of its rows, by a sequence of permutation of its columns, and by a sequence of permutation of its symbols of each column. The general problems which investigate from orthogonal arrays is the existence for which values, that is, for which values of the numbers, row, column, strength, and levels does an orthogonal array exist. And construction, the next problems is constructions. If we know that some orthogonal array exists, can we construct the orthogonal array in such parameters? The third problem is non-isomorphic classes. Find the numbers of non-isomorphic orthogonal arrays for given parameters. And the next two problems is more precisely for our investigation, to find the smallest possible number of rows of orthogonal arrays, and for a given number of runs to know the largest number of columns that can be used in an orthogonal array. So, in our investigation, we use the investigate the distant distribution of orthogonal arrays and obtain some restriction of their distant distributions, and obtain after that the bounds on covering radius, the minimum distance, and so on. So let's see be an orthogonal MNQT. Here is the opposite MNQT orthogonal arrays, and here is the arbitrary points of the Hamming space. The distant distribution of C with respect to this point is the n+1 tuple W, where WIX is the number of points, which is the distance I from the point X. Denoted by P of X and R of X capital, the set of all distant distributions with respect to the internal points, that is the points of the array, and for the external points, that is for the points which belongs to the array. We use this difference between internal and external points to obtain some specific restrictions on the distant distributions. It's clear, of course, that all distant distributions are PC and RC together. Let us explain of our examples these distant distributions. For orthogonal arrays with parameters 8, 5 to 2, there is only one distant distributions for all 8 internal points C. There is 2 distant distributions for external points. In particular, there are 8 external points with distant distribution null 0, 4 to 0, 1. And one of these points is 1, 0, 0, 0, 0. And there are for 16 external points with distant distribution 0, 2, 2, 2, 2, 0. And one of these points is 0, 1, 0, 0, 0. So we consider several ways, all of them variation of a classical results of Delsart's theorem and theory, for computing the distant distributions of the orthogonal arrays. We need to explain a classical family of orthogonal polynomials. Indeed, the Kravchuk polynomials are important in explanation of properties of codes on orthogonal arrays in Hamming space, and the Kravchuk polynomials are defined as the following kind. So, also the polynomials satisfy the following 3-term recurrence relations with initial conditions K0 and K1. Every polynomial, it's important for us that every polynomial of degree less than equals to dimension n can be expressed by the following way, where in particular the important coefficient f0 can be written as the following kind. So, the third proof that if C be an orthogonal MNQT orthogonal arrays and X be arbitrary points of the Hamming space, and if W is the distant distribution of C with respect to X, then the following equality holds for every K from 1 to 2. The equivalent kind of this theorem can be written by theorem 6. Let C be an orthogonal array with the distant distribution W with respect to the distance to point X. Then, for any polynomial f of degree at most t, the following equality holds. So, the importance of theorem 6 was observed by Fazik Levenstein in a more general settings where it was used for obtaining bounds on the minimum distance and covering radius of designs in polynomial metric spaces. Following further this idea, Voivolenkov and Kulina introduced certain system of linear equation with van der Monde matrices Tj power I for some j, and Tj is the different distance of the chemic space of T plus 1 equations and n plus 1 unknowns, whose solutions are all distributions from P sets P and R respectively. Thus, all feasible but not necessarily occurring distant distributions from P and R can be computed for reasonable values of the parameters Q and T and cardinality M. Denote by PF, RF, and WF the set of all feasible distant distributions to the internal, external, all points of the given orthogonal array respectively. In fact, we look to obtain their subset P, R, and W, but in many more cases, it's known only the set PIF, RF, and WF of this orthogonal array C with given parameters. Furthermore, the initial set can be further reduced by investigation of the relations between C and its related orthogonal arrays, and this will be discussed in more detail below. So, the aim of our talk today is obtain the upper bound, the minimum distance and covering radius of orthogonal arrays. And for an orthogonal array in n-dimensional having space with QSAM levels, its minimum distance is defined the following way, and its covering radius is the following number, respectively. Okay, we try to obtain, to improve, or to obtain the exact value or to improve the bounds on these two important characteristics of orthogonal arrays, C. There are simple relations between the minimum distance and the covering radius and the external distribution in the set P and R respectively. Let's see an orthogonal array in n-dimensional Hamming space and let P and R be the set of internal and external distance distribution of C, X explained above. The minimum distance and the covering radius of C satisfy the following two conditions, where the minimum is taken for the minimum distance of all distributions P from P of C, and for the covering radius, the maximum is taken over all distributions R from the distributions of external points respectively. So the following theorem holds. Let's see be an orthogonal array, and let P F and RF be some set of feasible internal and external distance distribution of C. The minimum distance of C satisfies the following bounds, and where both the minimum and maximum are taken over all distant distributions for internal points. In particular, if the set PF is an one-element set, then equalities holds in both sides. The covering radius of C satisfy the last conditions, where the maximum is taken over all distant distributions for external points. Now we present some generally related orthogonal arrays and their distant distributions. Let the distant distribution of C with respect to X be W, and the distant distribution of C prime with respect to the point X prime be W prime, where C prime obtained from C by deletion one of its columns without community restrictions, the first columns we use. For every fixed I from 0 to n, the Wn times n submatrix of an array C, which consists of the rows of C at a distance I from the point X, is called I block. Let's fix a column of the orthogonal array C. We denote by yi bar, yi, the number of non-zero elements, the zeros respectively, in this column, and the row of the I block. if we rearrange the rows of the arrays so that, let us explain over the construction, so that in the first columns we have first 0, after that 1, after that 2, and so on, after in the end q minus 1. From the properties, you will know that we obtain C0, C sub 0 orthogonal arrays with parameter m over q n minus 1 qt minus 1. And in the next theorem, we prove that their distant distributions is present with y. And we obtain also the orthogonal array C0 bar with this parameter and with y bar distant distribution. So the following theorem holds. Let C be an orthogonal arrays and C prime be an orthogonal m n minus 1 qt, which obtained by C as the construction above. Then the following system of linear equations with variables y and y bar, there is a unique solution of the following kinds, very different to explain easily, but moreover, the vector y is the distant distributions of the orthogonal array C0 and with respect to the point x prime, and the vector y bar is the distant distributions of the array C0 with respect to the point x prime. That is, we know that distant distributions y and y bar belongs to this set or this set respectively. After applying the above relations over the initial sets from this all distant distributions of the arrays, orthogonal arrays from the constructions, some of their elements rule out. We obtain more relations between the orthogonal array C and its related, which do not discuss here because the formulas are more and more difficult to explain. So Theta Weinen gave an upper bound for the covering radius of a binary orthogonal array as a function of its strength equivalent dual distance. This was generalized by Fazekas-Levenshtein for polynomial matrix poise as the following general bounds for covering radius. The first three bounds from this theorem are present in these slides. This is first, this is second, this is third. For strength 3, the upper bounds of covering radius. Manev obtained several different systems, all equivalent to the system from Theorem Delsart and equivalent for Theorem 6. These variants can feasible facilitate fast computation or provided more convenience expression. We work to the following set of systems and use this. Bumova and myself, with our PhD student Teris Ramai, proved the following theorem. We have the following covering upper bounds for covering radius. First, which values for all orthogonal arrays, and its refinement from 1, which is valid if the conditions n minus 2 greater than q minus 1 is fulfilled, and further, if n great in this number, then we refinement the upper bound one more, that is the covering radius less than equals to n minus t minus 2. So it is well known that for minimum distance there is the following upper bounds. And this bound is attained by the MDS codes. In fact, orthogonal arrays of index 1 are exactly the MDS codes. In more general settings, Levenshtein proved the bounds, the following bounds. Recall that T and the strength and dual distance, there is this relation between them. Sorry. Let's see be an orthogonal M and Qt of index lambda greater than 1 and minimum distance d. Then we know we obtain the following upper bound, which more refinements if also n minus t greater than lambda q minus 1 over lambda minus 1 is fulfilled. This is our new upper bounds, and all of the obtained bounds and present here can be seen in our databases, where you now have databases for binary orthogonal arrays and for ternary orthogonal arrays. And here we explain some easily examples. If we consider the ternary orthogonal arrays with 27 points, with 11 dimensional Hamming space, with strength 2, we have the following bounds for minimum distance and covering radius. If also the number of the columns one more from the previous, that is, we have the ternary orthogonal arrays with parameters 27, 12, 3, 4, then the minimum distance is equal to 8 and covering radius less than or equals to 7. And if we consider a binary orthogonal arrays with parameters 128 points, 9 to 5, then we see that the covering radius and the minimum distance are 2, respectively. Our future work is to obtain exact values of new refinements for bounds on the covering radius and minimum distance of the orthogonal arrays, respectively, and to update our databases of unknown and computed distance distributions and bounds, and of course to construct databases for the arbitrary Q. So this is the reference which our sites. Thank you for your attention.
Thank you, Maya. Thank you for finishing correct on time as well. And now, are there questions to the speaker? Seems like there are no questions. Let's call the speaker once again. Okay, I think it's about time to begin. Our next speaker is Fabrizio Martino from the University of Palermo, and he'll talk about central polynomials and exponential growth of the codimensions. Fabrizio.
Well, thank you. I hope all of you can hear me. So first, I want to thank the organizing committee for giving me the opportunity to give this talk today. And secondly, I am very honored to participate at this conference that is dedicated to Professor Drensky. Professor Drensky was and still here is a fixed point of my area of research interest. So since I was a PhD student of Giambruno, I started to study several papers by Drensky, and his deep results and theorems are nowadays crucial in the topics I work with. Also, I am not to mention his didactic skills. So for example, I want to say to all of you that I am a big fan of his book, Superalgebras and PI-algebras, that was reading, as Plamen remembered yesterday. I think must be almost mandatory for the people who work with algebras with polynomial identities. And it is so much important, for example, that I call it the gospel. Of course, I am a student of Giambruno, so for me the Bible can be only the book of Giambruno and Zaitsev, but I mean no offense. Well, I want to thank Professor Drensky for his works that inspired all of us. But let's talk about mathematics. Let's talk about the central polynomials and the exponential growth of the codimensions. Well, I'm starting with some basic definitions that actually some of them were given by Francesca in the. Very good. Okay, some of them were given by Francesca in her talk, so we're going to make it fast. So we need any field. We need an algebra over the field. And we need the corresponding free algebra over F generated by the countable set of variable X in order to give the definition of polynomial identity. A polynomial identity is an element of the free algebra for an algebra A, is an element of the free algebra that values always 0 under all substitutions of the elements of the algebra. So very quickly, if A is commutative, then x1, x2 minus x2, x1 is a polynomial identity for the algebra A. What we do is collect all the polynomial identities into a set that we denoted by ID of A. There is actually a T ideal, so it is an ideal of the free algebra that is stable under the action of all endomorphisms of the free algebra. So, at least historically, the first problem that arises just after the definition of polynomial identity is the following: find the polynomial identities satisfied by a given algebra. This is actually a very hard, in general, hard problem to solve. So Regev in 1972 introduced a quantitative approach in order to gather at least information about the number of polynomial identities satisfied by an algebra. So in characteristic 0, he defined the codimension sequence in the following way: as the dimension of the vector quotient space of multilinear polynomials reduced modulo the multilinear identities. Well, in the same paper, and then in a paper by Kemmer, were proved several properties about codimension sequence. In particular, we know that for a PI algebra, such a sequence is exponentially bounded or grows polynomially. Moreover, Kemmer gave conditions for which the codimension sequence grows polynomially. And such a result was extended also several years later in various settings, such as graded algebras, algebras with involution, pseudo-involution, special Jordan algebras, but also algebras with super involution, graded involution. There are a lot of results in this direction that I didn't write here just for lack of space. So the codimension sequence is exponentially bounded. So as Francesca said, we can define the so-called PI exponent as the limit of the nth root of the codimension sequence. Such limit was conjectured by Amitsur, exists, and it is an integer. And the Amitsur conjecture was proved positively first in the setting of algebras, associative algebras without any addiction structure, by Giambruno and Zaitsev in 1999. Such a result was also extended in other settings. Here we list an example of results. And the main point, how Giambruno and Zaitsev proved such results. They proved in particular that the PI exponent equals the maximal dimension of a so-called admissible subalgebra. So a theorem by Kemmer states that any associative algebra has the same polynomial identities as the Grassmann envelope, E of B, of a finite dimensional superalgebra, B. So we write B by following its Wedderburn-Masseff decomposition. We have B1 plus Bn that are simple superalgebras, and J, that is the Jacobson radical. So they proved, in fact, that the PI exponent exists, and moreover, it equals such a dimension. As an admissible subalgebra is a subalgebra like Bi1 plus Bik, where these are the distinct simple components that appears in the Wedderburn-Masseff decomposition of B, subjected to this condition here. Well, let's talk about central polynomials. They are the main object of this talk. Central polynomials are a natural generalization of polynomial identities. In particular, a central polynomial is a polynomial whose values belong to the center of the algebra. So, for example, all the polynomial identities of a PI algebra are central polynomials. Or if A is commutative, then all polynomials from the free associative free algebra are central polynomials. Or for the algebra of 2 times 2 matrices, the commutator square x1, x2 is a central polynomial. Finally, for the Grassmann algebra, E, the commutator among x1, x2 is a central polynomial. So we saw that all the polynomial identities are central polynomials. Well, they are central polynomials, but actually not so much interesting. So we define central polynomials that are not identities as proper central polynomials. Well, in our previous example, all the polynomial identities are central polynomials. Of course, they are not proper. In the second, in case of commutative algebras, all the polynomials of the free algebras are central. Well, among them, there are proper central and not proper central polynomials. Of course, it depends from the polynomial you are choosing. In the third example, 2 times 2 matrices, this is a proper polynomial, a proper central polynomial, as in the fourth example, this polynomial for the Grassmann algebra, they are proper central polynomials. It is not so difficult to find a non-zero evaluation of these polynomials that lie in the center of each algebras. So the existence of the proper central polynomials is not granted in general. In fact, there exist algebras with no trivial center, but with no proper central polynomials. For example, Giambruno and Zaitsev in 2018 proved that the algebra of block upper triangular matrices has no proper central polynomials. Why we study central polynomials? We study central polynomials after a conjecture by Kaplansky of 1955 that states that the algebra of matrices have proper central polynomials for all m. Such a conjecture was solved separately by Formanek and Razmizlov in 1972 and 1973. And I want to cite here also several works by Drensky among 1985 and 2013, in which the minimal degree of a proper central polynomial of the matrix algebra was studied. At the end of this path, the final result is that such a minimal degree is less or equal to n squared plus 3n minus 2 divided by 2. Well, so what we do? As we did for the ordinary polynomial identities, we collect all the central polynomials inside a set that is a T-space. It is not a T-ideal more. And of course, find the basis for the T-space of central polynomials is, I think, an even harder problem compared to the problem to find the basis for a T-ideal of identities. So here there are 2 examples of papers in which a basis for the T-space of central polynomials were found in case of the Grassmann algebra. So we use the quantitative approach of RegF. So we define such quotient spaces. So P and ZA, the multilinear polynomials reduced by the central polynomials, and delta n of A, that is the most interesting object. There are the multilinear central polynomials reduced by the multilinear identities. So delta n of A actually is the vector space of proper central polynomials. And we can attach to them the dimensions. So we define the central codimension sequence as the dimension of the first quotient vector space, and the proper central codimension sequence as the dimension of the second quotient vector space. Given this definition, we have that the ordinary, we can call it the ordinary codimension sequence, is the sum of such 2 sequences. So we can gather information about the codimension sequence, the original codimension sequence, by studying such 2 sequences, of course. Moreover, since we know that the codimension sequence is exponentially bounded, also are the central and the proper central codimension sequences. So we can define, as we did for the codimensions, for the ordinary polynomial identities, we can define the exponents. So we can define the central exponent and the proper central exponent in analogy with the ordinary case. So some problems arise. First, such limits exist. Are we able to compute them? Are they integers? Can we compare them with the ordinary PI exponent? I will present to you now results from 3 papers. The first one in the setting of associative ordinary algebras by Giambruno and Zaitsev of 2019. And in the settings of algebras with involution, from a paper by myself and Professor Carlarizzo, and in the setting of algebras with G grading, where G is a finite abelian group, there is a result contained in the paper by myself, Professor Carlarizzo, and Professor Daniela Lamattina. We studied the existence and the integrability of the central exponent and the proper central exponent. So what they did, Giambruno and Zaitsev, they translated the definition of admissible subalgebra in the setting of central polynomials. So they said that a centrally admissible subalgebra E of B is a direct sum of simple superalgebras, so the simple components that appear in the Wedderburn Maltsev decomposition of B. B is, I recall, a finite dimensional superalgebra. So this is a centrally admissible subalgebra if there exists a multilinear proper central polynomial f with the property that the first k variables are evaluated in the first k Grassmann envelopes of the first k distinct simple components here, and the other s minus k, where s is the degree of f, can be evaluated in any elements of the Grassmann envelope. So this is the new definition of admissible subalgebra. So they proved that the proper central codimension sequence delta n of E of B is upper bounded and lower bounded by an exponential function like d to the n, where d is the maximal dimension of a centrally admissible subalgebra. They also proved that in case E of B has proper central polynomials but has no centrally admissible subalgebras, then the proper central codimension sequence is eventually zero. So in this case, the exponent must be zero. They proved the following results. So the proper central exponent exists. It is a non-negative integer that is less or equal to the PI exponent. So what about the central exponent, x plus z of A? Well, it turned out that dealing with the central exponent is simpler than working with the proper central exponent. I think it's worth mentioning that the crucial role in this proof is played by the so-called minimal variety of exponential growth. A minimal variety of exponential growth is a variety whose codimension sequence grows as d to the n, for example, but with the property that that every proper subvariety has an exponential growth like t to the n, where t is strictly less than d. I lined such a situation because I know that minimal varieties are nowadays a very studied object among the mathematicians that work in PI theory. So about the central exponent, we have this result. The central exponent exists. It equals the PI exponent in case the PI exponent is greater or equal to 2. Otherwise, it can be also 0. Why can be 0? Because of the existence of the commutative algebras. There exists a commutative algebra that with PI exponent equal to 1, but of course with the central PI exponent equal to 0 since it is commutative. Very good. So about algebras with involution, I remember I worked joint with Professor Carlarizzo. We work with algebras with involution. So we have an algebra with an involution defined on it. We have the definition of central star polynomial in analogy of the definition of a central polynomial in case of ordinary algebras. Here we have to pay attention to the symmetry of each variable. So a variable that is symmetric with respect to the involution must be evaluated in a symmetric element of the algebra. And a variable that is skew-symmetric with respect to star must be evaluated into a skew-symmetric element of the algebra, but the definition is, the philosophy of the definition is almost the same. So we can define, as in the previous cases, we can define such three quotient vector spaces. So we have Pn star of A, Pn star Z of A, and among them delta n star of A, the proper central star polynomials. So we can define such three quotient vector spaces. We can define the three codimensional sequences We also know that the star codimension sequence here is exponentially bounded. We know a lot of information about it. And so first, I want to remember that also that this relation holds also in this case. And since the star codimension sequence is exponentially bounded, it makes sense to define the star exponents and its brothers, the central star exponent and the proper central star exponent. The existence and the integrability of the star exponent is well known. With Carla Rizzo, we worked on the central star exponent and the proper central star exponent. So we translated the definition of centrally admissible star subalgebra in case of algebras with involution. Here, I have to remember that by a result by Aljadeff, Giambruno, and Ekarazik, any star algebra has the same polynomial identities of the Grassmann envelope of a finite dimensional superalgebra with superinvolution. So B is a superalgebra with superinvolution of finite dimension. We write it by following its Wedderburn-Malzer decomposition, and so we have to give the definition of a centrally admissible star subalgebra. As in the previous case, even here we have just to pay attention to the symmetry of each variables, but the philosophy that is beyond this definition is the same, actually. Well, so what we do, we proved that the star codimension, the star proper central codimension sequence is lower bounded and upper bounded with the exponential function d to the n, where d is the maximal dimension of a centrally admissible subalgebra. And even in this case, we proved that the star central exponent exists. It is a non-negative integer, and it is less or equal to the star exponent that we know how to calculate. About the central exponent, we proved the following results. So the central exponent exists, it equals the star exponent when the star exponent is greater or equal to 3. Otherwise, it can be also 0. Even here, there are the commutative algebras. Commutative algebras with involution can be of exponent 2, star exponent equal to 2, but being commutative has the central exponent equal to 0. I mean, for example, f plus f with the exchange evolution is an example of commutative algebra with involution, whose exponent is 2, actually. Well, finally, I present very quickly a result with Professor Daniela Lamattina and Carla Rizzo about group-graded algebras. We work with finite abelian groups. We have a G-graded algebra. We know that any G-graded algebra has the same polynomial identities of course, there's a mistake here, is IDG of A, is not E of A. So any G-graded algebra has the same polynomial identities as the Grassmann envelope, yes, of a G times Z2 graded algebra of finite dimension. This result holds also in case G non-abelian. And so we proved, as in the previous cases, that the proper central G-graded exponent exists. It is a non-negative integer, and it is less or equal to the G-graded exponent. Analogously, the central graded exponent exists. It equals the G-graded exponent, or it can be 0. Here, the problem of the commutative algebra is bigger because there are a lot of commutative algebras in case of G-graded algebras that can have a G-graded exponent equal to any integer. I mean, well, so these are the references. And I hope I've done. So thank you for your attention.
Thank you, Fabrizio. Are there questions to the speaker?
Yeah, Fabrizio, can you go back to maybe 3, 4 slides, go down or up? Here. So, so it's a confusion here, right? N1T and T1, T2. So you're not claiming anything about the polynomial, right?
No, I'm not claiming anything about the polynomial factor.
Okay.
And of course, there is a mistake here because it's T1 and T2. Yeah.
Okay,
yeah.
okay. Thank you.
Okay. Thank you for your comment.
Are there other comments or?
To make a small comment about the minimal degree.
Yeah.
The central polynomials. So this is not my this conjecture Formanek, but the story is that as Niv Kasparian,
So I don't know if I am the problem, but I don't.
No, I lost you.
Matrices. We did it by hand using some techniques which were very nice. And even 15 were only able to find our to confirm.
I think Professor Drensky is saying that
I had some problems with the connection. But if I asked her to, do you listen now?
More or less.
Okay. Her problem was to find that there are no central polynomials of degree 8 because Formanek, he conjectured that the minimal degree is n squared for n by n matrices.
Yeah.
But we were not able to prove this. And she told me, okay, there should be some central polynomial. She wrote the central polynomial. But then I proved that this is really a central polynomial. And Formanek, his comment was, you spoiled the nice conjecture, because the nice conjecture was that n squared is the minimal degree. Yeah. Then in joke, I told him, you see, you know what happens in 1, in 2, in 3. And you can conjecture, you can make a quadratic function using 3 points. And he conjectured this here degree, claiming that this is also in the spirit of other conjectures for polynomial identities of matrices, and in particular the Nagata-Higman theorem. And then with Julia Maria, and then I myself, we constructed central polynomials of degree n minus 1 squared plus 4. For 3 and 4, this is okay, but even now we don't know which is the minimal degree of the central polynomials, and for matrices of size 4 and more, even we don't know whether they are polynomial identities of degree. What you have here, n squared plus 3n minus 2 divided by 2. This is simply a conjecture.
Yeah.
Okay, thank you.
Yeah. Thanks for your comment. It's a very interesting problem, actually, because we know what the minimal degree of a polynomial identity for any matrix algebra is, but about central polynomials, there are some conjectures and examples. Yeah.
Thank you, Fabrizio. Are there other comments? Well, let's thank the speaker once again. We're about to begin our second part of the first session. And our speaker is Tsetska Rashkova.
Greetings to everybody at the International Conference Trends in Combinatorial Ring Theory, dedicated to the 7th anniversary of Vesselin Drensky. What Drensky you have given to all of us has many different aspects. A famous scientist, a great leader, a significant man, a close friend, and yet more and more. You had spent so much personal time to introduce me in PI theory, to help me in starting writing papers on myself, to encourage me both in science and everyday life. You are really my scientific father, but you became and remain a real friend of mine. Though feelings, not words, are important, I want to say some. Drensky, please accept my gratitude, my appreciation to be with you and around you in the bigger half of my life, to share with you and Zhenya so many unforgettable moments. Congratulations. Be healthy, Master Drensky. And my talk, just to see what's the situation. Identities generated by standard polynomials for some matrix algebras with Grassmann entries. I want to start with the remarkable year of 1950 and the result of Amitsur and Levitsky that the standard polynomial of degree 2 times n is a polynomial identity of minimal degree for the matrix algebra of order n over a field of characteristic 0. When we endow the matrix algebra with additional properties, namely with an involution star, we could consider star polynomial identities either in symmetric variables or in skew symmetric ones. And there is a good survey of Bresar and others giving the best up to now partial solution that the smallest degree of a standard star polynomial identity in symmetric variables in the matrix algebra of order 2 in power m, for S being the symplectic involution, is indeed 2 in power m plus 1 minus 2.
Excuse me, I think we are not seeing the presentation, or it's only me?
You are not seeing it?
I cannot see it either. I was thinking it was my problem, but I cannot see it.
We can actually.
I mean, we see the first page, but it's not moving. Probably you are going further.
Tsetska, can you scroll? Can you move the slides?
I don't see any slide at all, actually.
Just to see here.
Here at the Institute of Mathematics, we can see the presentation, but we can see you now. Can you share again?
Is it seen now?
I can see here.
Yeah.
Me too.
Can you try to scroll down or up? Okay.
I started with this, stating this theorem and the result of Bresar and others. And the general situation of the matrix algebra over the Grassmann algebra, or in other words, with Grassmann entries, is a next topic of investigation. And in 2001, Perel and Tregev proved that the algebra of order n over the Grassmann algebra does not satisfy the nth power of the standard polynomial of degree m for any M. I want to mention the identity of algebraicity for matrices over the Grassmann algebra, defined by Jenno Sigeti in 1997, and the following proposition proved by him, that the standard polynomial of degree 2 times n in power 2 with the written variables here is an identity for the matrix algebra of order n. In 2015, a new approach was introduced by Laszlo Malarkey and others, namely an embedding of the M-generated Grassmann algebra into a 2 in power m-1 matrix algebra over a factor of a commutative polynomial algebra in m variables. And applying this procedure, it was proved that the standard identity of degree 2 in power m times n is a polynomial identity for the matrix algebra of degree n over the m-generated Grassmann algebra. Many results about the standard identity and its degree could be seen in a work of Peter Frenkel in 2017. Here I state this proposition, start with this proposition, that the standard identity of degree k equal to 2 times n times the whole part of m over 2 plus 1 holds in the matrix algebra over the m-generated Grassmann algebra. In the case when n and m are equal to 2, he found a better result, which is proposition 5. Another proposition of Frenkel is that the standard identity of degree k, 2 times n plus the whole, the integer part of m over 2 minus 1, does not hold in the same as in proposition for algebra if the base ring is a field of characteristic either 0 or a prime strictly greater than 2 times the integer part of m over 2. In the same paper, a question was asked about the degree function of the standard identity. Namely, does the standard identity of the shown degree hold in the considered matrix algebra? In 2019, it was shown by Balash and Messerosh that the minimal degree of a standard identity in this, when the matrix algebra is over the 2 generated and on the 3 generated Grassmann algebra, is 4 times n minus 2. In 2011, Onofrio de Vincenzo and Plamen Kushlukov studied the superalgebra M sub 1, 2 with this involution. And as it was said in some of the talks in the morning, for this involution, we could consider symmetric and skew-symmetric elements of the algebra. And the two authors proved that this superalgebra satisfies the identities of minimal degree written in preposition 7. The first for the symmetric elements and the second one for the skew-symmetric elements. And all these results show that finding the minimal degree of a standard identity could be naturally generalized to consider polynomials who are generated by standard polynomials. And I give some results in this direction. I will not speak in details about the definition of the Grassmann algebra. Here, the generator of the T-ideal is given, the result of Karkovsky and Regev in 1973. And in 2001, this proposition about this identity in the Grassmann algebra. Here, I want to point some classes of algebra satisfying identities of the considered type. The first algebra is the n-dimensional matrix algebra of the matrices of this type, where the coefficients are fixed elements of the field. And for it, the following identities were found, written here, these three. And I want to say that the proof of the existence of such identities is a result of, in a way, intermediate result, that this algebra satisfies the identity, the triple commutator multiplied on the right by a variable. When we have n equal to 3, one identity more, the third degree of the standard polynomial of the third power of the standard polynomial of degree 2 holds as well. Another matrix algebra considered is the 2 times n in power 2 dimensional matrix algebra of matrices of this kind. We have elements on the zeros are the elements here, to say in the left part, under the and above the two diagonals, and the same on the right side. The matrix algebra of these matrices satisfies some identities, some of which are written here. The last two, when n is even or odd number. The next matrix algebra considered was the 4 times n plus 1 dimensional matrix algebra of the matrices of this type, having non-zero elements in the first row and in the first column, and in this middle row, to say. This algebra satisfies these identities. The standard of degree 2 and 3, and the corresponding powers written here. As it was said for the previous, for the proposition 11, firstly, we prove that the considered algebra satisfies this identity, and in not as a calorie, but significantly use the satisfaction of this identity, these two were proved. About the problem in the work of Peter Frankl. The investigations were made using this embedding introduced by Laszlo Marchi of the M-generated Grassmann algebra, and for an arbitrary for this initial condition, we consider representation of R over omega, which is an injective K-algebra homomorphism. A special CT constant traced representation is introduced, and here are the details when we have M equal to 2. This is the CT representation, where these are coefficients of the field with characteristic 0, and this is the LDL of the commutative polynomial ring generated by these two monomials. Here is given a proposition from the work of Marchi, theory, really theorem 3.1 in his work, defining this special CT representation of ME, and the fact that these concrete assignments given here define a CT representation of the M+1 generated Grassmann algebra over this special matrix algebra. And applying this proposition, we form the representation in this special kind. And here I give the representation of the three variables, nu sub 1, nu sub 2, and nu sub 3. And when M is equal to N equal to 2, using the system Mathematica, we form these 4x4 matrices. Here they are given in a way suitable for the product, and only for the matrix A3, here, for example, is given the block way representation of it, namely this one. And for these special matrices, we calculate the standard polynomial of degree 6. We constructed, then calculated, and as we are working in the ideal generated by A in power 2 and B in power 2, used these two notations instead of Z sub 1 and Z sub 2, we confirm the proposition fine in the considered partial case. But when we consider M equal to 2 and N equal to 3, and analogously find 8 matrices with which we work using the System Mathematica, here is the matrix X1, and here is its block presentation. We found that the standard polynomial of degree 8 is not an identity. Here is given really that two entries are not zero in the considered modulo, the ideal generated by A in power 2 and B in power 2. And this helps us to give the following interpretation of problem 1 by Frenkel, namely that if the standard identity of degree K holds in this algebra, then K has to be strictly greater than this number. Some two prepositions here are given. In the case when we consider the matrix algebra of order 2 over the Grassmann algebra, in the case when we have the transpose involution, these three identities in it, in skew-symmetric variables, and if you have the symplectic involution, these identities in the matrix algebra really as identities when the variables are symmetric ones. And I want to finish with some facts concerning the above mentioned result of Vincenzo and Kushukov in the case when we consider the algebra of matrices of this type, where these block matrices have even entries and these two odd entries, really subalgebra of M sub 2, comma 2. This mapping is really an involution in this algebra. We formed two matrices A, B in power, the involution of A times B and the product of, the product of phi B and phi A, And we prove that it's really an involution. And even in this case, we found that the same star polynomial identities, the first one in symmetric variables and the second one in skew symmetrics, are the same as the one given by Vincenzo and Kushlukov. This is my talk. Thank you for your attention.
Thank you, Tsetska. Are there questions or comments? Seems like there are no questions, so let's thank the speaker again. Okay, I think it's time to begin with the next talk, the last talk of the morning session. So it's going to be given by Luisa Carini from the University of Messina, and she'll talk on the classification of multiplicity-free products of sure functions.
Okay,
Luisa, go ahead.
thank you. Can you hear me?
Yes, we can hear you very well.
Okay, so first of all, I would like to thank Plamen Kotchetov and all the organizers for giving me the opportunity to deliver virtually a lecture and to celebrate the 7th anniversary of Vesselin Drensky. Many congratulations to Vesselin for his brilliant scientific career. I'm very pleased and honored to be among Vesselin's friends and co-authors. Okay, now I will start talking about the symmetric polynomial. Is a well-known polynomial which is invariant under all permutation of the symmetric group of degree n. A well-known and classical symmetric polynomial is the elementary symmetric polynomial. We have a few examples, like we have the elementary symmetric polynomial of degree 1 and 3 variables, the first one. The second is the elementary symmetric polynomial of degree 2 and of degree 3. Another important polynomial is symmetric, is the power symmetric function. The power symmetric function of degree k in n variables is the sum of all k powers of the variables. And we have the first few of this polynomial are the following. Sure, in his thesis, PhD thesis that was published in Berlin in 1901, studied the irreducible polynomial representation of the general linear group, and he was able to compute the characters of this representation that are symmetric polynomials and were named after him sure functions. So sure functions named after his sure are symmetric polynomials indexed by partition. In order to give the combinatorial description of sure functions, I need to recall a few basic definitions and a preliminary result. A partition of a positive integer n, this is the notation, it's an increasing sequence of positive numbers such that their sum is equal to n. The sum is also called the weight of the partition, and the number of non-zero part is called the length of the partition. A geometric description of the partition is given by the Ferrero-Young diagram indexed by the partition lambda. This is best shown with the following example. If we consider the partition 1, 2, 3, 3, 4, 6 of 19, so the length is, the non-zero part are 6, so the length is 6, is obtained the Ferrero diagram indexed by this partition by drawing one box in the first row, two boxes in the second row, three boxes in the third row, and so on, which are left justified. This is the French notation of the Young diagram, and I will use this notation during my talk. A common strict tableau or semi-standard tableau is a filling of the Young diagram with positive integers in such a way that the weakly increase in the rows from left to right is strictly increasing the columns from bottom to the top. Here is an example. If we consider the partition 1, 2, 3, 4, 4 partition of 14, T here is an example of column strict tableau indexed by this partition. It's a filling of the boxes with numbers from 1 to 5 in such a way that they strictly increase in the column from the bottom to the top and the weakly increase in the rows from the left to the right. It's also possible to associate to the column strict tableau or the semi-standard tableau a weight monomial. How can we get this weight monomial? We replace the numbers in the boxes by the corresponding variables, and we take the product all over the boxes. For example, instead of 1, 1, we will have x sub 1, x sub 1 2 times, so we will have x1 to the square. Then 2 appears 3 times, so we have x2 to the third power, and so on. So this is the weight monomial associated to this column strict tableau. In this way, we have all the ingredients to define the sure function indexed by the partition lambda. In any set of variables, provided the number of variables must be greater or equal to the length of the diagram associated to lambda. So the sure function is the sum of all weight monomials associated to all column strict tableau of shape lambda. We show a simple example. If we want to compute the sure functions in 3 variables associated to this partition of 3, we have to draw all the column strict tableau, which are 8 in this case, and then consider all the weight monomials associated to all of them. So in this case, for the example, in the first column strict tableau, the monomial x1 to the square x2, here it is, then plus x1 to the square x3, plus x2 to the square x3, and so on. So this is the sure functions in 3 variables indexed by the partition 1, 2, or 3 of 3. Basically, there are 3 fundamental products of the sure functions: the ordinary products, the Kronecker products, and the platism. It can be shown that these 3 products can decompose in the sum of sure function with the certain coefficients. Only for the first product, there is a combinatorial interpretation and a rule to compute these coefficients, which is known the Littleburg-Richardson rule. In fact, these coefficients are called the Littleburg-Richardson coefficient. Instead, for the Kronecker product and the platism, there are no such rules, and only a few special cases have been solved so far. There is also a connection, an important connection between the theory of symmetric function and the representation theory of the symmetric group, which is given by the Frobenius map. More precisely, if we consider a map between the center of the group, this Frobenius map is a basic isometry between the center of the group algebra and the space of homogeneous symmetric functions of degree n, which sends an irreducible character indexed by lambda in a sure function is indexed by the same partition. Through this Frobenius map, the Kronecker product of 2 sure functions indexed by lambda and mu respectively are the image of the inner or tensor product of 2 irreducible characters. So when we decompose the tensor product or inner product of two reducible characters in the sum of reducible character indexed by a certain partition, the coefficients are the same that they occur in the decomposition of the Kronecker product of the two sure functions. So, why it's important to compute all these coefficients? So the Littlebrook-Richardson coefficient, the Kronecker coefficients, and the Platism coefficients, because they occur in several areas: in invariant theory, in representation theory, in the theory of symmetric functions, in PI theory, in physics, and also in quantum information. There is a problem. One problem in the symmetric function theory, which are the products of sure functions that are multiplicity free. In other words, products for which every coefficient in the resulting sure function expansion is 0 or 1. If we consider the Littlebrook-Richardson coefficient, so we start with the first product, which is the ordinary product of sure function. So we wonder when this can be equal to 0, 1. But this is well known. There is a well-known rule. When we multiply a sure function indexed by a partition lambda, a sure function indexed by partition mu of length 1, we get a well-known example of multiplicity-free product of sure functions, like in the following example. So if we consider the sure function indexed by this partition lambda equal to 2, 2, 3 by a sure function indexed by this partition, this product decomposes in the sum of 5 summands, which are sure function indexed by these diagrams by this partition, and all the coefficients are equal to 1. But this is nothing else that the celebrated Peary rule, which gives an elegant method for expanding the product of a sure function and a single row of sure functions in terms of sure functions. Notice that all the coefficients that occur in the expansion are equal to 1. This rule was originally stated in the setting of Schubert calculus by Mario Peary and named after him. This is the picture of Mario Peary, and this is another easy example of the multiplication of two sure function. One is indexed by the partition 1, 2, or 3, and the other is indexed by the partition 3. So we see that all the yellow boxes, they go around the diagram of 1, 2 in such a way that there are no two yellow boxes in the same column. Stembridge, Richard Stembridge, in 2001, in this paper, Multiplicity-Free Products of Sure Functions, which was published in Annals of Combinatorics, he completely solved the problem of classification of the ordinary products of two sure functions. In fact, in this paper, we classify the products of sure functions that are multiplicity-free, products for which every coefficient in the resulting sure function expansion is equal to 0 or 1. This is the theorem. The product is multiplicity-free, the ordinary product, if lambda mu is one-line rectangle, or lambda is two-line rectangle, and mu is a fat hook, where a fat hook is a partition of this form, or vice versa, or lambda is a rectangle, and mu is a near rectangle. By near rectangle, we mean a partition lambda obtained from a rectangle by adding a single row or column. Or if lambda and mu are both rectangles. This is very nice result due to Stembridge. Okay, now we go to the next. So the problem for the ordinary product is completely solved. Now we go to the next product, and also in this case, we wonder when this G can be equal to 0, 1, for which partition lambda, mu, gamma, we have only in the decomposition, we have 0, 1. We have to be, in this case, lambda, mu, and gamma are partitions of the same positive number n. I would like to mention that very recently, Greta Panova from University of Southern California, on July 9, 2021, gave a very interesting talk on the mysterious Kronecker coefficients of the symmetric group. This was in the seminar of algebra logic in Sofia. And if someone is interested to know all the updates on the Kronecker coefficients, could visit this link, and where there are video slides of this very nice lecture. Also in this case, the problem of the classification of multiplicity-free Kronecker products had been completely solved recently in 2017. Bresar and Baumann, in the paper Multiplicity-Free Kronecker Products of Characters of the Symmetric Group, which was published in Advances in Mathematics, they provide a classification, a complete classification of multiplicity-free inner tensor products of a reducible character of symmetric groups. This is their theorem. I don't want to go through all the details, but just some remark. Also, the partition involved are like rectangles or two-row partitions, and there are some exceptions considered. Okay, so the last product is the platism. We'll see what happens in case of the platism. The platism was introduced by Littlewood in 1950 in the context of compositions of representation of the general linear group. A platism of two sure function, this is one of the notation used for the platism, can be thought as the character of the composition of two reducible polynomial representation of the general linear group. Littlewood proved this theorem if we have a lambda partition of M and mu partition of N. The platism decomposes in the sum of a sure function indexed by partition N, which is a partition of the product of the two integers, positive integer, with a certain coefficient. The basic problem is to compute these coefficients. Now, this is another notation for the platism. The platism here is the sum of the sure function indexed by gamma. So the problem of computing the coefficient is one of the fundamental open problems in the theory of symmetric functions, and this proves to be very difficult. Essentially, there are explicit formulas for the coefficients in a few special cases. We say that the platism is multiplicity-free if every coefficient in the resulting sure function expansion is 0, 1. A well-known example of multiplicity-free platism was given by Littlewood, where he proved the following remarkable simple formulas. If we multiply S indexed by the partition 2 by S indexed by partition N, this platism is equal to the sum of the sure function indexed by lambda, where lambda is two parts. This is a partition of N with two parts which are even. In case we consider the S with the 1/2, partition of 2, instead this we have the same decomposition, but the partition of 2n has only two parts which are odd. So these are well-known example of multiplicity-free platism, and we have some simple example of the decomposition in case n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5. This is a very simple decomposition according to a Littlewood theorem. In case we consider n 1 to the n, we have the following decomposition. In the case n equal to 2 until n equal to 5. This result by Littlewood was generalized by Carbonara, Remmel, and Young in 1995 to the case when lambda is a hook, so it's a hook shape. And they were able to also to find the expansion of this platism, to compute the explicitly the coefficients, and also in this case we have an example of multiplicity free platism. Later, in 1998, Remmel and myself also we proved this theorem where there is a very nice combinatorial description of the platism in case the partition inside the lambda is a rectangle. These are given, also these platism are multiplicity free, as you can see, the coefficients are equal to 1, and they are given in terms of certain balance, Kn balance shape that I don't have the time to describe now. This result was this result was translated differently in this paper by Mizukawa Yamada in their paper Rectangular Sure Function, the Basic Representation and Finally Algebra. They gave another description. Also in this case, the problem of multiplicity-free platism has been completely solved. So Bresar, Baumann, and Paget, they in their paper, which is in archive in March 2020, have classified and constructed all multiplicity-free platism of sure functions. More specifically, they have proven the following classification theorem. Also in this case, mostly there are partition of rectangular partition or near rectangles, and there are also some exceptional products. Anyway, I don't want to spend time to go into the details. So at the end, the classification of multiplicity-free product is completely solved for the three products: ordinary products, Kronecker, and platism. So the picture is now complete. Here there are some references. And I would like to finish my talk by sharing with you a nice picture that was taken at the Weizmann Institute of Science during the International Conference on Growth Phenomena in Associative and Lie algebras, because many of these participants are here in the audience, I think. There is Vesselin here. There is also Formanek. Formanek was mentioned several times during the talks. And there is Plamen Koshlukov. It's me. Bakturin, Francesca, Mishenko, Antonio, Pretrogradsky, Misha, and Zayshev, and Onofrio. Thank you for your attention.
Thank you, Luisa. Are there questions?
I want to make a small comment that usually the people who do PI algebras, from them the partitions, they decrease and not increase as in the talk by Luisa. For example, the partition is not 1, 2, 3, but 3, 2, 1.
Mm-hmm.
So this means that this is the so-called English or British way to present the partition metric functions. The French partition is the French way of partition. This is to stay on your with your head down, legs up, and looking in a mirror. Here, in the notation of Luisa, she got only one reflection, so you should stay in the PI men should stay on their hands and the legs, but without a mirror. So this is not the French. The French is a little bit more complicated.
Okay.
But it was really very nice talk. Thank you very much, Luisa.
Very nice. Thank you. Thank you.
And also in this picture you can see. In this picture, you can see that the PI men, they go from a conference to a conference in almost the same, the same people, but also there are, of course, some new people here.
Yes.
And since we mentioned our seminar, I advertise our seminar of our department, Algebra and Logic, which is usually on Friday.
Yes.
And this is still online. So, many people of the people who are here, they have information about the talks, but also you all are welcome. This is free, no registration. You simply can go directly to the talk. Okay, thank you.
Yeah, you're welcome.
Are there other comments? Well, let's thank Luisa for the nice talk once again.
Okay, good afternoon, everyone. It's a pleasure to open the afternoon session, and it's a pleasure to introduce the first speaker, Eli Aljadeff, who is going to talk about on forms of G-graded simple algebras.
Okay, thank you very much. It is a real pleasure to be part of this conference dedicated to Vesselin. Thank you very, very much, Vesselin, for your support over the years. And thank you, Plamen, and the entire committee that invited me. So I will talk on forms. The problem will be related to forms of G-graded simple algebras. Of course, I will explain the problem. And somehow I use it as an excuse to explain a different approach to this problem, which is via verbally prime or G-graded verbally prime T-ideas. This is an important topic in PI theory, something that Francesca mentioned in the morning. So I will give some preliminaries, then explain the main problem, which will be related to G-graded algebras. Then I will say a few words why we are interested in G-graded G-gradings on central simple algebras. Then I will recall very briefly verbally prime T-ideas, and then enter into the main topic, which is G-graded verbally prime T-ideas, and then go back to the main problem. And this is joint work with Yakov Karasik. So we all learned that K-central simple algebras, finite dimensional, over a field K. If we extend the field to the algebraic closure, we get matrices, n by n matrices for some n. And it is well known that this characterizes central simple algebras. We say that central simple algebras are forms of matrix algebras. Since division algebras are K-central, are central simple algebras, then of course division algebras are also forms of matrix algebras. But less obvious, but still very well known, that every finite dimensional simple algebra, K-central simple algebra, every finite dimensional over an algebraic closure, in other words, matrices, has a division algebra form. Always you can find the division algebra form. And more than that, you can find always a division algebra form over fields that contain algebraically closed fields. Okay, we know that there exist finite dimensional, that there exist division algebras of every degree, but there exist division algebras of every degree over a center that contains an algebraically closed field. Okay, this will be important later. And equivalently, the generic object that corresponds to n by n matrices over any field is a division algebra. Okay, this is the well-known generic division algebra of degree n. So the main problem is what happens in the G-graded case. And G is a group. So we want to replace finite dimensional simple with finite dimensional G-graded simple. That means that the product is non-zero and has no non-trivial G-graded two-sided ideals. And we replace division algebra form with G-graded division algebra form. That means that non-zero homogeneous elements in D are inverted. So if we try to do what I said before in the ungraded case, if D is a finite dimensional G-graded division algebra over its E center, I call it the E center, just the intersection of the center with the E component, and I take the algebraic closure, then extending scalars, we get a G-graded simple algebra. And we can ask, following the ungraded case, does every finite dimensional G-graded simple algebra have a graded division algebra form? Okay, similarly to the ungraded case, and the answer is no. I mean, in a very strong way, the answer is no. So the main question is which graded simple algebras do admit a G-graded division algebra form? And I will address the problem in case the characteristic is zero and G is a finite group for good reasons. And the reasons is that I will use the classification of verbally prime G-graded T ideals. And along the way, we use PI theory and also in particular Kemmer theory, and more specifically G-graded Kemmer theory. And this we know in characteristic zero and for finite groups. This is a joint work with Benanti. So from now on, F is a field of characteristic zero and algebraically closed. A few words about motivation. Group grading on central simple algebras is perhaps the main key for studying them. Cross-product gradings, for example, realizes the very well-known isomorphism between the Brauer group and the second cohomology group, where this is the absolute Galois group and this is the separable closure. Every case central simple algebra is Brauer equivalent to a cross-product algebra. Okay, so we have a finite Galois extension, G is the Galois group, and alpha is a cohomology class. This realizes this isomorphism between the Brauer group and the second cohomology group. Another type of grading, which later we will call it a fine grading. This is the grading appearing in symbol algebras. So I write Z mod n, but we should think of this as multiplicative cyclic group of order n. So this is the algebra generated by X and Y, where X to the n is equal to an element in A, a non-zero element in K, and Y to the n is equal to B, and XY is a primitive nth root of unity, YX. Okay, so X and Y, XY is equal to zeta n yx. And this is a central simple algebra, a case central simple algebra. And probably the most important theorem in the classical most important theorem in Brouwer theory is Merkur-Suslin theorem that says that the nth torsion of the Brouwer group, if the primitive nth root of unity is in the base field, then the Brouwer group is generated by such algebras, by symbol algebras. Another important motivation is that some of the main open problems in Brouwer group theory are related to these gradients. For example, one of the important open problems is every Brouwer class that we know that is represented by a cross product, is it represented by an abelian cross product, where the Galois group is abelian? Okay, so this is not known. So let me now say a few words about the verbally prime ideas in the ungraded case. And I know that many of you know it very well, but I want to explain something that will be later important. So verbally prime T ideals, verbal prime ideas is a T ideal such that for whenever you have two T ideals, I and J, that are contained in gamma, either I is in gamma or J is in gamma. Okay, this is the definition. But you can define it in terms of polynomials. So gamma is verbally prime if and only if for every two polynomials, multilinear, in this joint set of variables, if the product is in gamma, then at least one of them is in gamma. Okay, so this is the definition in terms of ideals, and this is the definition in terms of polynomials. The proof of the equivalence is not difficult in both directions, but one direction is really obvious. I will show you in a minute. Whereas the other direction, as I said, not difficult, but less obvious. So the obvious direction is that polynomial, definition in terms of polynomials implies definition in terms of T ideals. So here is the proof. Assume definition in terms of polynomial holds, and suppose by contradiction that I times J is in gamma, but I and J are not contained in gamma. Then taking P in I and not in gamma, and taking Q in J and not in gamma, PQ will be in IJ, but IJ is in gamma, and so we get a contradiction because P is not in gamma and Q is not in gamma. Let's see the other direction. The other direction, we suppose that I times J is contained in gamma implies, this is the definition in terms of ideals, and we want to show that this is true for polynomials. So we take a product of two polynomials in gamma. We can consider the T ideal they generate as a product of two polynomials. This definitely will be contained in gamma because gamma is a T ideal. But what we want is to separate P and Q. We want to have that the T ideal generated by P times the T ideal generated by Q, they are contained in gamma. If we knew that, then by the condition on ideals, one of the ideals would be in gamma, and therefore the corresponding generator also would be in gamma. Okay, but in order to separate, we need somehow to be able to multiply from the right of P and multiply on the left of Q. We can multiply on the left of P and then we multiply on the right of Q and can use the T operation but we cannot multiply on the right of P. But with suitable T operations, okay, by manipulating the T operation on multilinear polynomials, we can obtain that if a polynomial is in a certain T ideal, then the Lie commutator will be in the ideal. Okay, this is easy, but I think very, very nice calculation. But now we are allowed to multiply on the left. This means that, in fact, we are allowed to multiply on the right. And this is the way to separate this product and get the product of the two T ideas. Okay, I emphasizing that because this will become not true later. Okay. Okay, so now, as mentioned by Francesca, what are the verbally prime T ideas? These are ideas of identities of n by n matrices. So the ideas of identities of the Grassmann envelope of a super simple algebra. This is Kemmer. And now we pass to the G-graded. We pass to the G-graded PI theorem. So we have a G-graded algebra. We consider the free G-graded algebra over F with the natural grading. We have G-graded polynomials, and mainly we will consider homogeneous polynomials. We have G-graded identities. These are polynomials that become zero upon a graded evaluation. So variables can get evaluations only from the corresponding homogeneous component. So it is easier to be an identity. G-graded T ideals, okay, they are closed under G-graded endomorphisms. And G-graded verbally prime T ideals via the definition of G-graded T ideals or via the definition of homogeneous polynomials. Okay, so we have the two definitions. But note that the T operation must keep the homogeneous degree. Okay, so we cannot replace with the T operation now a variable x sub g with x sub g z sub h, where h is an arbitrary element of the group. But we can only substitute with x sub g z sub e, right? In order to keep the same G-graded, the same homogeneous degree. So here there are two arrows that tell me go up. Okay. So now when I do the Lie commutator, I can do the Lie commutator with variables that correspond to the E component. I cannot do it with arbitrary variables, homogeneous variables. So practically I can multiply from the right here or from the left here by elements of the E component. But this will not be enough. This will not be enough to get this result. So in fact, the two conditions are not equivalent. The condition with ideas, the condition with polynomials are not equivalent, are far from being equivalent. The condition with polynomial is much, much stronger. So here is the consequence. The corresponding definitions of verbally prime, namely via T ideas, are not equivalent. Okay. So let me say what are the verbally T ideas in terms of ideals. the definition in terms of ideals. So gamma is a T-ideal of identities of a G-graded algebra, which is PI is an ungraded algebra. Always we take the condition that the algebras are PI as ungraded algebras. In algebra, a G-graded PI algebra could be non-PI, it's an ungraded algebra. But at least I know almost nothing about this kind of algebras. And here we have a theorem of Perel and Bergen that the verbally prime T-ideals in terms of T-ideals, okay, are precisely in the fine case the T-ideals of identities of a finite dimensional G-graded simple algebra. And in the non-affine are the T-ideal of identities of the Grassmann envelope of an algebra which is Z2 cross G graded simple. So if you take A that is Z2 cross G graded simple, and you take the Grassmann envelope with respect to the Z mod 2, you can view this algebra as a G graded algebra, and these are exactly the verbally prime T-ideals. So what about the verbally prime in terms of polynomials? We called it strongly verbally prime. Okay, so we give an answer in case of where the T-ideal is a T-ideal of an affine algebra, or equivalent where the T-ideal contains a Capelli polynomial. So because strongly verbally prime implies verbally prime, it is sufficient to consider T-ideals of identities of finite dimensional algebras which are G-graded simple. Because by Perel and Bergen, in the fine case, these are the verbally prime, and our condition is stronger. So we can assume that. So how do they what is the form of the G-graded simple? So let me give you two examples. One is a twisted group algebra, generalization of a group algebra. It is definitely G-graded simple. It's even a G-graded division algebra. Every homogeneous element is invertible. Non-zero homogeneous element is invertible. H is a subgroup, and alpha is a second cohomology. This is the product given by alpha. Another G-graded simple is just take matrices. Matrices is simple, so it will be G-graded simple, and put an elementary grading. Elementary grading is a grading where the EIJ element has homogeneous degree, which is GI inverse GJ. So we take a tuple, G1 to GR, as the sizes of the matrices, and we give this homogeneous degree to the EIJ elementary matrix. So this is the grading where the elementary matrices are homogeneous. And well-known theorem of Bakhtiurin, Segal, and Zaitsev, they classified finite dimensional G-graded simple algebras. They do it more general than that, but this is enough for us. The characteristic 0 and F algebraically close. And they say that every G-graded simple algebra is a combination of the fine grading and the elementary grading. So it's the tensor product of these two examples that I showed before. So this is a little bit unprecise, so here is something more precise. Every such algebra has a presentation, so we have to choose a subgroup of G, a subgroup H of G. We have to choose a second cohomology element, then we have to choose an R tuple. once we have this data, and this data is not unique, but in a sense is quite unique, and we can say more precisely, but no, and not enter into that. We have the tensor product of the two algebras, and the basis elements U sub h tensor Eij form a basis of the tensor product, and the homogeneous degree is Gi inverse H Gj. Okay, so the Gi inverse and Gj come from here, and the H comes from here. Okay, so this order is important. Okay, in the non-abelian groups. Okay, so in the abelian it doesn't matter. And as I mentioned before, the E center is just the intersection of A with the center of A with the E component. So with this terminology, we have the following theorem. Let gamma be a G-graded T ideal. Suppose gamma contains an ungraded Capelli polynomial. This is the way to say that it's the ideal of a PI affine algebra. Then gamma is strongly G-graded verbally prime if and only if gamma is the T ideal of A, where A is G-graded simple with presentation PA that I mentioned before. And the presentation must satisfy that H is normal in G. Each H coset is represented the same number of times in the tuple. That's the second condition. And the third condition is that alpha, the cohomology, second cohomology element, must be invariant under the action of G. Okay, there is an action because H is normal, so there is an action of G on H. There is an action on the second cohomology group with the trivial action on F. And alpha must be G invariant. These are the strongly G-graded verbally prime T ideas. So if you want, these are the verbally prime T ideas in terms of polynomials. So for example, if G is equal to the group of two elements, the strongly verbally prime super T ideals that contain Capelli are the FZ2 tensor matrices, one of the examples of super simple algebras, or unlike the general situation where you can have here different values, here we must have the same value. Otherwise, it is not strongly verbally prime. And this is the application. The application is that to the original theorem, that A is finite dimensional G-graded simple algebra. Let A be a finite dimensional G-graded simple algebra, and let PA be the presentation. I say here a presentation, and the theorem is true for one presentation, and it will be equivalent for every presentation. So if the conditions are satisfied for one presentation, are satisfied for every presentation. Then A admits a G-graded division algebra form over a field K. But now there is a condition which contains enough roots of unity. So A admits a G-graded algebra form over field K, which contains enough roots of unity, if and only if gamma is strongly verbally prime. So precisely when the above conditions 1 to 3 on PA are satisfied. Okay, so let's try to understand it. And so we ask, is it possible that an algebra admits no G-graded division algebra form, satisfying the above conditions on roots of unity, but does admit such a form if we don't impose any condition in K? Okay, so let me explain. The condition that is equivalent to strongly verbally prime is that there exist graded forms if you assume that you have enough roots of unity. But, so here I ask, is it possible that an algebra doesn't admit such a form, like here in the theorem, but still admits? This was our original problem. Our original problem didn't care about roots of unity. So the answer is yes, it can happen. So we need a more general notion of G-graded strongly verbally prime. Okay, so here is a fact. It is possible that the T-ideal gamma inside the free algebra over F is defined over a field K. That is, the T-ideal is obtained from a T-ideal here after extension of scalars. And multilinear polynomials P and Q with coefficients in K satisfy the verbally prime condition. In other words, P times Q is in gamma K, then one of them must be in gamma K. But gamma is not strongly verbally prime. In other words, if you remove the condition that the coefficients are in K, this will not be true. So you can get two polynomials in the product and none of them being in the T-ideal. So this cannot happen in the ungraded case. In the ungraded setting, this phenomenon cannot happen, and this is why I mentioned at the very beginning that you have division algebras containing algebraically closed fields. In other words, as many roots of unity as you want. So we need to know that for such algebras, every T-ideal of identities has a unique minimal field of definition. Okay, and this is true. Okay, these T-ideals have a unique minimal field of definition. And for such T-ideals, we say that gamma is essentially verbally prime if for every P and Q homogeneous with coefficients in K, K the minimal field of definition, we have our condition. So here is the theorem. Let gamma be a G-graded T-ideal. We want to classify essentially verbally prime. Let gamma be a G-graded T-ideal of T-ideal of identities of a G-graded simple. Then gamma is essentially verbally prime if and only if the following three conditions are satisfied on any, or if you want, on every presentation of it. So here again, we have a presentation. And as before, H must be normal. H, the cosets of H must appear with equal frequency in the tuple. But the third condition is different. Okay, so I call it 3 prime. The cohomology class alpha must be G invariant. Also, before I use the terminology that it should be G invariant. But now G invariant means something different. So what does it mean? We know that G acts on H because H is normal. So it acts on the Schur multiplier, which I call M of H. Now I recall by the universal coefficient theorem that the F is algebraically closed, so the second cohomology group is isomorphic to the home of the Schur multiplier with coefficients in the units of the field. And now, if alpha is our cohomology class that appears in Bach-Turing, Segal, and Zaitsev presentation, and we look at the map from MH to F that corresponds to alpha, and we consider the kernel, which is inside MH, is a subgroup of MH, then I want this kernel to be G invariant. This is the definition of G invariant. Okay? So our final answer to the original problem is that let A be a finite dimensional G-graded simple algebra over F, then A admits a G-graded division algebra form okay, with no condition, if and only if gamma is the T ideal of identity, gamma, the T ideal of A, is essentially verbally prime. So precisely when the conditions 1, 2, and 3 prime above are satisfied. And we may ask a different question: when does A admit not a G-graded division algebra, but a division algebra in the ordinary sense, which is G-graded? This is more difficult. Okay, but this is, as I wrote here, another story. So thank you very much, and congratulations, Vesselin.
Thank you very much for the wonderful talk. Are there any questions?
What about, for example, Henselian value gradings arising from?
Sorry, I cannot hear.
What about?
Can you compare?
Who is talking?
Ivan Kotchetov is talking from the room, so I'm not sure whether you can hear me.
Is there some information concerning gradings which arise from valuations from fields? For example, division algebra over simple algebras over Henselian field, something like this.
Simple algebras over?
Fields with Henselian valuations. In this case, there is some theory which associates graded division algebras with this. For example, with the division algebra of such a field, graded division algebra is associated. Other results of this kind for such
So I'm not sure I understood. You are interested when the ground field has also a G grading?
Well, it is in doubt when it is in doubt with for example, Henselian valuations, which
yes.
the existence of a certain grading.
Yes, I never thought about this. Yes, I don't know. I cannot say. So with this additional structure, you want an additional structure?
Yes.
Yes, I understand. No, I don't know. I have never thought about it.
Are there any questions? Okay, let's thank Eli again. It's a pleasure to introduce the second speaker for the afternoon, Matej Bresar from the University of Maribor. He's going to talk about zero product determinism answers.
Okay, thank you very much. Thank you. I would like to thank the organizers for inviting me here, and of course I would like to congratulate Vesselin and wish him all the best. I only regret that we have to do all this online. It would be much nicer to be in Sofia offline, but that's how it is. So I will talk about, as you can see the title, so-called zero product determined algebras. I suppose that most of you do not know what this is. My intention now is to give a survey of this theory that has been developed over the last 15 years. And I promise to do my best to be easy to be understandable. So whenever I will come to the point where things become technically more complicated, I will stop. My idea is just to point out the main ideas, because I know that in this audience here, this is probably not the topic that many of you know. Okay, so let me start with the definition. You can see the structure of my talk above, so I will first explain the definition. Then I will talk about the motivation, applications, and things like that. So I will try to explain why this concept that I will now introduce is interesting. And in the last part, I will finally show what are examples of algebras which appear under the title of this talk. Okay, so let's start with the definition. So we start with an algebra A over a field F. So let's fix this. And we do not assume that algebra is associative, so it can be non-associative. In fact, this theory has been developed. Let's say that half of the theory is for associative algebras and another half of the theory for non-associative, and by non-associative I basically mean Lie and Jordan algebras, maybe some other partial results elsewhere. Okay, so A is an algebra, and we start with a bilinear functional phi. Phi is a bilinear functional, and now let's consider two conditions on this bilinear functional. The first one is that whenever the product of two elements, x and y, in this algebra is 0, then phi vanishes on this pair. Phi of x, y is 0. And the second condition, the condition B, says that phi somehow arises from the product, meaning that there exists a linear functional tau such that phi of x, y is equal to tau of the product x and y. And it is trivial that the second condition B implies the first condition. Of course, if phi of is such a form, and if x times y is 0, then phi will be 0. And the algebras in which we will be interested in are those algebras in which the converse is also true. So A is a zero product determinant algebra, and I will always shorten this as ZPD. So I will use this abbreviation all the time. ZPD means zero product determinant. So it's a zero product determinant algebra if for every bilinear functional phi, A implies B. Because this definition is essential for everything what I'm going to talk about. So if you are lost here, you will be lost for this talk. So let me repeat once again this definition. So what does it mean that an algebra A, associative or not, is ZPD? It means that whenever a bilinear functional phi has the property that it is 0 on each pair of elements whose product is 0, then such a functional, bilinear functional, is necessarily of such a form. It arises from the product and some linear functional. So somehow philosophically, this algebra is determined by zero products, because if you know all zero products, then somehow you have a control on the product. There's just one product possible. Okay, so I will explain later on why this is interesting, etc. Let's now just try to memorize this definition here. So I should say that this theory of zero product determinant algebras has two branches, two parallel branches with a lot of interactions, but still different. And the other branch is the analytic branch. The definition is the same, but we have to assume that these functionals phi and tau are continuous, and this continuity really makes a difference. In this conference, I will focus on the algebraic part, and this is easy for me because I'm an algebraist, so this is somehow natural. I feel much more comfortable. But I have to say that this also has a downside, because the analytic branch of the theory is richer in some ways. There are other ways how to state this definition. Here I will mention a few equivalent conditions. well, you see, the second condition, so A is ZPD if and only if this condition 2 is fulfilled. And this condition 2 essentially just means that this linear functional tau is well defined. So it's just a well-definedness problem. Now, when we have bilinear maps, there's always a possibility to express the condition via the tensor products. And so this is a tensor product characterization. So what does it mean that the algebra is ZPD? It means that every expression of such a form, every element in the tensor product of A and by itself of such a form, where the sum xy, yi, 0 can be expressed for some elements z and w in such a form where now for each j, zj, wj is 0, not the sum, but for each pair of elements, their product is 0. And the last condition, so it is essentially the same as the definition. So this condition 4 reads just as the definition. The difference is that this bilinear, so that we don't have a bilinear function, but any bilinear map into any vector space X. But otherwise it's the same. Now tau is not a linear functional, but a linear map. We could take this as the basic definition because this is something that we always use. The reason why only functionals appear in the definition is that perhaps in this way the definition is shorter and more elegant. It's easy to prove this, that the proof is routine. Of course, if we have this analytic context, then we have to take continuity and Banach spaces and so on. I will not talk too much about this. I should also mention that there is almost identical notion, which also appears throughout the literature, an algebra or Banach algebra with property B, where this condition that phi is of this form arising from tau is replaced by this one. You see, these two conditions are almost equivalent. So the upper condition obviously implies the lower condition in associative algebras. I should mention this. In associative algebras, and if the algebra is unital, then the lower condition implies the upper condition. But there are some differences in algebras without unity, and somehow, unfortunately, there are two names for almost the same algebras that appear in the literature. But I will use this. So zero product determinant algebras, ZPD algebras, and in fact, I just wrote a book about this. It was published less than a month ago. It practically appeared at the beginning of September. So I surveyed the theory, as I said, that was developed over the last 15 years. And the book is divided into 3 parts. The first part is the algebraic part. The second part presents the analytic branch of the theory. And the third part deals with various applications to different mathematical problems. So I should say that the main contributor to the analytic branch of the theory was my colleague and friend Armando Villena. I'm mentioning this because it was our original plan to write this book together, but then for different reasons he changed his mind, but he was helping me all the time. And although I was also involved in this development of the analytic branch, and we have many joint papers with him, I don't want to take all the credit for this, so that this is the reason I want to stress his role especially in the analytic branch of the theory, which is so on the surface quite similar to the algebraic one, because the ideas are at the beginning quite algebraic, but then this continuity condition really makes a big difference. So although I'm an algebraist, I've been working on this sort of functional analytic problems with algebras throughout my career. And it's always been my goal to show to functional analysts that one can also use only algebraic methods, 99% algebra and 1% of analysis, and you can produce an interesting result. But now this is not the case. So in this theory, it has turned out that the analytic part was really essential. So the analytic results are more impressive. Okay, so now I will talk, as I announced, on the motivation. So essentially, I will speak about, I will show several examples where this ZPD condition naturally occurs and can be applied. So in a way, I'm doing sort of experiment, because this is not maybe the natural way of talking, because one should first give some examples to show that this notion is not empty. But somehow, because I'm assuming that you're not familiar with this theory, I think I should spend more time on the motivation. So in these examples that are following now, I will try to show that knowing that some algebra is ZPD can be useful. So first, about, as written here, original motivation. This is sort of a personal remark here. About 15 years ago, I was involved in working on two papers which were completely different topics. One algebraic, so central simple algebras, and another one analytic C-star algebras with my Spanish colleagues, and here the first one with my friend Peter Schemel. But what was common to these two problems, completely different, was that in both of these papers, the breakthrough was made by considering, instead of linear maps, which were studied, some bilinear maps, basically satisfying this condition that appears in the definition I gave you. So essentially, using the nowadays terminology, using the fact that some algebras are ZPD, we were able to solve two different problems. And at that time, I started to be interested in this condition, which looks just like some technical condition. And so eventually, together with my colleagues, we were somehow creating or developing the theory of this. But now, some three concrete examples I would like to show. So please believe me that ZPD algebras exist, and now let's show, provided that they exist, why they can be useful. So in the first example, I will consider so-called zero product preserving linear maps. You see, they are defined like this. Whenever the product is zero, if x and y is zero, then t of x times t of y is zero. If our algebra is a Lie algebra, then instead of saying zero product preserving, it is more natural to say, and it's usually said so, commutativity preserving maps, because then you know that the product is zero, it means that the elements commute. And the obvious goal is to describe the form of such a map, and the natural problem is to show that T is maybe not a homomorphism, but close to a homomorphism. So why this problem? This problem has a long history in both functional analysis and pure algebra. There are more than 100 of papers that have studied a version of this. In functional analysis, it actually goes back to Stefan Banach, who considered this in his classical book from the 30s, some special case which he needed to study isometries, but somehow then it has spread throughout different parts of mathematics. So just this general type of a problem. And having this ZPD condition, it is pretty obvious that this problem can be studied. So, proposition. I call this proposition, but it's a triviality. You see, this is the proof that's written below. That's the whole proof. So, if we have this linear map that preserves zero product as above, then it is of such a form for some linear map tau. And what is the proof? We just apply the definition of ZPD algebra to the map phi of xy is t of x times t of y, because this condition is fulfilled. And so, by the very definition, we get that t is of this form. And now this reminds us immediately on homomorphisms. And if we assume additionally that A and B have unities, and if we add the artificial assumption, I should say that one is preserved, then it is clear that just take y to be 1, that t is equal to tau, so we get the desired conclusion. T is homomorphism. But without this assumption, t of 1 is 1, then the problem becomes non-trivial. But somehow, in a way, a breakthrough has been made, so we can somehow come closer to the desired conclusion that T is a homomorphism if the algebra is ZPD. So in this slide, I will show two concrete theorems that were proved by using this idea, and they are connected to the original motivation I was talking about. So we have a finite dimensional central simple algebra of dimension different from 4. This condition is necessary. And assuming that a linear map preserves commutativity, then it follows that T is either of what we call standard form, somehow obvious expected form. Phi here is either a homomorphism or an anti-homomorphism. Lambda is a scalar, mu is a linear functional, and such a map definitely preserves commutativity. Or if this is not the case, then we have another trivial, obvious possibility when T preserves commutativity, simply when its range is commutative. All elements in the range commute with each other. So the main stop of the proof was actually this proposition here, which is very simple. So you just have to prove that some algebras from this theorem are ZPD, which is not very difficult. But somehow the breakthrough was made in this way, because after that the proof was still very, very long. But somehow this was just the main idea how to approach. And at that time, when this was proved, this was an open problem among experts. So it was a good result at that time. And the other analytic problem, now we have Banach algebras, etc. So I will be here, I will be very brief. Again, we assume that our algebra is ZPD, and now we have so associative algebras, the usual associative product, and in the above theorem we had the Lie product. And now if we have surjective continuous zero product preserving map, then this is almost a homomorphism. So it is just the composition, the product of a homomorphism and a map W called a centralizer, which means that it satisfies this condition. If the algebra is unital, then this only means that W is the multiplication by a central element, invertible central element. And again, so the main idea was just to use the ZPD condition here. Okay. So the second example, now take an associative algebra A and consider the following problem. Is every commutator in an algebra a sum of square zero elements? Why this problem? Again, this is a problem with a long history. So in pure algebra, it goes back to Kaplansky and Herstein, and again in functional analysis, it was considered by many people. And it may not be entirely obvious when you see this problem that the ZPD condition can be used, but we will see immediately that it can. So proposition says that the answer is positive to this problem, to this question, if A is a ZPD algebra satisfying this minor condition, which is A square is A, which is definitely fulfilled if the algebra is unital. And the proof is very, very simple. Let N be the subspace of all elements that are sums of square zero elements. Consider the bilinear map defined as follows. And note that this map has the desired property that somehow preserves zero product. So if x times y is 0, then yx has obviously square 0, which means that yx belongs to n, and so phi is 0. And then using the definition of ZPD, it follows immediately that, you can see the proof here, maybe there's no need to give more comment, that any commutator lies in N, lies in this space. Okay, so this was the second example where it was very easy to use the ZPD condition, but maybe not obvious when you see the problem, like in the first example. And now the final third example where, again, the ZPD condition can be used, but it is not at all obvious from the problem that it can be applied. So that there is a more hidden way how it can be used. So let A be, as always, an algebra, associative this time, and M an A by module. A local derivation is a linear map such that for every x, there exists a derivation d sub x, such that d of x is equal to d sub x of x. This was introduced by Caddison about 30 years ago, and this is again a problem that has been studied by many, many authors after Caddison's seminal paper. So it appears again in functional analysis and in pure algebra, and dozens and dozens of papers were written on this. So just to have an impression of this definition, so if our dx is inner, then this simply means that every d of x is equal to the commutator of x and some element, but we don't know if this element A depends on x or is it fixed. We would like to it to be fixed somehow. So this is the goal, to show that local derivations are derivations. And what is the connection with the ZPD condition? Consider a pair of elements such that x, y, and y, z is 0, not a pair, 3 elements. And then you see x times d of y times z is equal to this by the definition of a local derivation, but now d sub y is a derivation, so we use the derivation law. And now we arrive at xy here and yz here, so this is 0. So local derivations always satisfy this condition. If this is 0, then this is 0, which is not something that appears in the definition of ZPD algebra. But there is a way how to use this definition. So we have this general lemma. If we assume that the algebra is unital and ZPD, and if we have a trilinear map satisfying theta satisfying this condition, then theta will always satisfy this. So it's a bit tricky how to prove this. I will not give a proof, but it is elementary in short. And so if we use this lemma for this special map, which written here, and we know that by the above remark that local derivations satisfy this, then we get this proposition that every local derivation on a unital ZPD algebra is a derivation. So we have this nice conclusion that the conclusion which we would like to have. So I gave just 3 examples of applications of the fact that an algebra is ZPD. In the book, I studied many more. Sometimes it's rather obvious that the ZPD condition can be applied, and sometimes it is hidden, like in this last example. So maybe it makes no sense to go through this list here and to comment. So, of course, if anyone is interested, I will be happy to explain details, but all this is in the book that I just wrote, and I think it's possible to download it from the Springer website if your institution has the access. Okay, and now the last part of my talk. I think I still have 13 minutes, if I'm correct. Please tell me if I'm wrong. I think there are 13 minutes. And so in this final part of my talk, I will speak about finally about examples. So far the theory was empty, so we don't know if such algebras exist. And even before I will start to speak about examples, let's just say that this class of algebras, ZPD algebras, is somehow behaves nicely. It is stable under various natural constructions. It is stable under direct product, also under infinite direct sums, but not under the infinite direct products. Then it is stable under the tensor products. So under homomorphic images, so the homomorphic image of ZPD algebra is again ZPD. Well, this is a bit subtle because it's written here under technical assumptions. In the associative algebras, this works quite nice, but maybe not in the algebras always. Also, ideals of ZPD algebras may be again ZPD, but it's not also, I cannot really say that this is always the case. Okay. So it's a nice, so this class of algebras behaves nicely from this just formal point of view. And now, again, finally to concrete examples. But first, a word about non-examples. Obviously, our algebra should have 0 divisors in order that all this makes sense. So in domains, we just don't consider domains in this theory. Well, the one-dimensional algebras are ZPD, but this is a triviality. So maybe just to mention, just as a hint, a slightly less obvious example, if we have something like differentiable functions, then if the product of 2 functions is 0, then the derivative of one function and times the second function is also 0. And this gives rise to non-examples. I have chosen here C1, but generally speaking, very often it turns out that showing that some algebra is not ZPD is based on the existence of some derivations which are not humble as inner derivations and so on. So some non-trivial derivations very often contribute to the fact that the algebra is not ZPD. Okay, but now finally, so far what I was talking about, the theory was empty because I gave no examples. So we still don't know if any ZPD algebra exists. If it doesn't, then I can stop my talk at this point, but well, it does. So consider this little lemma here. Okay, so consider a bilinear functional with the usual property. And then the lemma states that this set here is a subalgebra. The fact that it is a subalgebra is a triviality. You know, you can just, it is obviously a linear space, and if you take the product of 2 elements, you can move first one element S to the right-hand side, and then the other element just by the definition. So it's a subalgebra, this is trivial, and it contains all idempotents. this is again very, very easy, because if it's always fun to work with idempotents. It's difficult not to love idempotents. You just take this product, which is 0, and I'm assuming the existence of unity here for simplicity, and then you get two relations, and if you compare these two relations, you get that this E, an idempotent, lies in this set here. So that's all. Well, this little lemma is quite essential. First, it shows that if we have an associative algebra with unity, and if it's generated by idempotents, then it is ZPD. Why? Because if it's generated by idempotents, then R here is just an arbitrary element. So generated by idempotents, it's an algebra. Every element is a linear combination of products of idempotents. Okay, if you take Y to be 1 here, then you will get that f of x var depends just on xr. So we have this proposition here. Every algebra generated by idempotents is ZPD. Just as a prototype of such an algebra of matrices over any unital algebra is then ZPD, because such an algebra is generated by idempotents. There are, of course, many other different examples, but I will not talk about this here. Now, what about other examples? To my surprise, it has turned out, so I proved this some years ago, that in finite dimensions, well, if we deal with algebras with unity, without unity, we have many other examples, but with unity, it turns out that the converse is also true. So being ZPD is equivalent to the condition that A is generated by idempotents. And the proof just uses the classical theory of finite dimensional algebras, like lifting idempotents is one of the crucial tools, definitely. So it was kind of surprise. It looks like a nice theorem, because when you just see the definition of ZPD, it has nothing to do with idempotents, but it turns out that being generated by idempotents is equivalent to ZPD. But I still don't know whether I like this theorem or not, because there's something embarrassing here. I do not know of any infinite dimensional algebra unital which is ZPD but is not generated by idempotents. So this is still an open problem. I tried many things, but all the time I have a feeling that if somebody clever will look at this problem, or maybe will know also something that I don't know, some examples, and will arrive at these new examples easily. So I was unable to end together with my colleagues. So this is an open problem here. So somehow this associative case is somewhat limited here. As I mentioned a couple of times, the Banach algebra context is somehow much richer. I still have like 5 minutes, so I think I will just go through this very, very quickly. And I'm also not sure if you are interested in this, but just to give some impression. So here, the role of idempotents is played by so-called double power bounded elements. You can see the definition here. And together with my Spanish colleagues, we proved that the algebra, or better, its unitization, is generated by such elements, then it is ZPD. And this class of algebra satisfying this is very, very large. So all C-star algebras, one of the main classes of algebras appearing in functional analysis, then group algebras, Banach algebra generated by idempotents, etc. So this is really a very big class of algebras, and it's somehow surprising that all these classes of algebras can be, some problems on them can be studied by some sort of the same method. Now, a few words about Lie and Jordan algebras. About general Lie and Jordan algebras, we have just various sporadic results, so no general theory. So we have tried, you can take a Lie algebra and you can ask yourself whether it is ZPD or not, but we don't have some general method how to approach this. But for associative algebras, viewed as either Lie or Jordan algebras, there are some more conceptual results. Let me give this definition. We say that an algebra is zero Lie product determined. Now, A is associative, I should stress. A is an associative algebra, and if the derived algebra A-man, so you know what it is, so every associative algebra becomes Lie algebra under the Lie product, and the Jordan algebra under the Jordan product. So if this algebra is ZPD, then we say that the algebra is zero Lie product determined. And just an example of results. So the algebra of matrices over another algebra is ZLPD, but only if B is ZLPD. It was actually quite difficult to construct a counterexample that it's not always so. It's written here connection with Jordan derivations, but I think I have no time to talk about this. So it has just turned out that this problem is connected with the problem whether Jordan derivations are first derivations, and then the second problem whether they are inner. And we have a similar notion of a zero Jordan product determinant algebra, and it is and the results here are similar as for ZPD algebras. So I see that the chairman is here, so I'm assuming that my talk is more or less that I should finish, right?
No, you can.
But yeah, it is the last slide actually. So this is the work in progress. Well, you can see the definition here. This condition has appeared all the time in our examination of these algebras, but now the expected result is more complicated. So we need two linear functional, one acting on xy and another one acting on yx. And just recently, I showed that, maybe slightly surprisingly, that if we work in the context of finite dimensional simple algebras that are not division algebras, we have to exclude them because for them these problems are not interesting. Then this definition 2ZPD is equivalent to the definition to the concept of separability. And that's it. So thank you very much.
Thank you very much for the inspiring talk. Are there any questions?
Maybe one comment.
Yes.
First of all, I'm happy to listen this because there is a PI theory in polynomial identity. Next step is consider images of multilinear or some other polynomials. And this conditional mapping and conditional stuff make the situation for research more broad. And this way to make the research more broad, to put more broad question, this is a usual tool, very interesting tool to attack some other question, including investigation images of polynomials in some algebras. That's why I enjoyed the talk.
Okay, thank you. So thank you for this comment. So it would be great, of course, if there is some connection can be found.
Ideological connection.
What kind?
Ideological connection.
Ideological, okay. Yeah.
Are there any other questions? So let's thank Matej again.
Thank you. Thank you.
Now it seems it is time to start with the next talk. And Professor Bakhturin told me he was giving classes earlier, so probably he is in his car now returning home. And he should be online in probably some 10 minutes, I do not know. But then I'll substitute him and we'll present the next speaker. The next speaker is Professor Antonio Giambruno from the University of Palermo. And he is going to talk about polynomial identities and trace codimensions. It's a pleasure to announce his talk. Antonio, you have the floor. Please.
Thank you. Thank you. So first of all, let me say thanks to Plamen and to the organizing committee, because this meeting looks so nice and so well organized. I mean, it's amazing. It's really amazing. And such a care you have paid to Vesselin celebration. Okay, and then let me congratulate Vesselin on his anniversary and also on his mathematical achievements. I know Vesselin maybe from 35 years or more, and he has been an inspiration for so many young mathematicians in Italy, with whom he has also collaborated. So it's I consider Vesselin not only a good mathematician, but also a good friend of mine. So happy birthday, Vesselin. Let me go to mathematics. Let me go to mathematics. So polynomial identities and trace codimensions. First of all, let me give you a definition of trace. So my algebras are associative of a field and with a one. So we're assuming that the algebra is a unit element. So a trace is just a linear map that satisfies these conditions. So the first one tells you that the trace is in the center. The values of the trace are in the center. And that's all. So typical examples are matrices over a field and with the usual trace. But just be careful, because if your an algebra is commutative, any linear map will be a trace. See, any linear map will be a trace. So, but let me give you one more example. This algebra is commutative, but it has a Jacobson radical. And you can define a trace in the following way. So you see this trace, unlike matrices, the trace on matrices, on important matrices is 0, here is not, if beta is non-zero. And this is a strange example because this algebra is actually isomorphic to the polynomial ring in one variable over f divided by the ideal generated by x squared. And the trace, if you look at that in this algebra in that example, in that way, you will see the trace is something strange. Anyway, if you want to compute, for instance, the identities of this algebra, or find the generators of the ideal of trace identities of this algebra, it's not easy at all. And I remember there is a paper of Kozhukov, Iopolo Mattina, where they actually study such an algebra. And it's an absolutely non-trivial task to prove something. Let me just make a remark. What about traces on matrices? It's not hard. You can prove easily that any trace on matrices is just the usual trace multiplied by a scalar. Okay. So since you want to study identities with trace, you have to introduce the free algebra with trace on a countable set. What do you do? Well, you take the usual set of monomials, you take the usual free algebra, and then you introduce a formal trace, TR, that has the axioms there. Well, of course, you have to impose that on monomials, the trace behaves that way, right? These are the axioms you have to put in. And so you have, this is a free object, and actually, this is only the free algebra tensor with a polynomial algebra in those elements, trace of monomials. So that's a commutative subalgebra. Okay. So let me just fix the notation. The elements will be called trace polynomials, but if I have a polynomial where all the variables are inside some trace, then I'll call that a pure trace polynomial. So I say that a polynomial is a trace identity if vanishes under all evaluations when I have substituted this formal trace with the trace of the algebra A. If all the variables are inside the trace, then I call that polynomial a pure trace identity. Okay, then I have these two objects, which are the set of trace identities of the set of pure trace identities of a fixed algebra A. And this is an ideal, is invariant under endomorphism of the free algebra with trace. Okay, this is the usual setting. Let me give you some examples. If you have a polynomial identity and you take the trace, that becomes a trace identity. But maybe the trace identity will be trivial. But if you multiply by one extra variable, you will be sure that this will be a non-trivial trace identity. So that's one way of building up trace identities. Another basic example is the Cayley-Hamilton polynomial. Okay, so you have K by K matrices, you take a matrix, and you take its characteristic polynomial, which I call the Cayley-Hamilton polynomial. You remember that the coefficients of a characteristic polynomial are the elementary symmetric functions in the eigenvalues of the polynomial, of the matrix. Now, the eigenvalues are the elementary symmetric functions, the elementary symmetric functions on the eigenvalues. Now, Newton formulas are formulas that allow you to write the elementary symmetric functions in terms as polynomials in power sums. Power sums are here interpreted, there will be trace of powers of the matrix. In other words, these Newton formulas work only in characteristic 0 because they have denominators. So you can write the characteristic polynomial of a matrix as a polynomial whose coefficients are polynomial expressions in the trace of powers of the matrix. In other words, if you write the Cayley-Hamilton polynomial this way, this will be a trace identity for your algebra. So it will be a trace identity in one variable outside the trace and all the other variables inside the trace. Okay. Let's assume that the characteristic is 0 from now until the end of my talk. Now, let's just make it, this is a standard way of doing things. You take a permutation of Sn, and then you write it as the product of disjoint cycles, including one cycles. And then to this permutation, you associate a pure trace monomial, will be the product of the traces of the variables which are indexed by the cycles. Okay, here's a theorem proved by Razmislov and Procesi independently. They say that the idea of pure trace identities of K by K matrices is generated by this polynomial. So sine over Sk plus 1. So this is all permutations on, okay, it's a pure trace. There is another way that if you look at the ideal of identities of pure trace identities, this idea is generated, trace identities is generated by the Cayley-Hamilton polynomial. Actually, these two formulations are equivalent. You can pass from one to the other. Let me show you how you can do that. So first, let me fix some notation. So MTN will be the space of multilinear trace polynomials. So these are linear combinations of expressions of this type. So you have some variables inside the trace and some variables outside. And let me call this trace codimension. So as usual. And now let me define the pure trace elements. So this will be PTN. So here all the variables are inside the trace, and this polynomial are multilinear in above and here, in the sense that every variable appears only once in every monomial. And we call this the pure trace codimension of A. Okay. First of all, like in the ordinary case, what is the relation between the group algebra of the symmetric group and the space of pure trace polynomials? Okay, well, first you just decompose the group algebra of Sn as a sum of two-sided ideals, which are indexed by partitions of n. And then you establish this map that maps sigma to that monomial that I wrote before. And this is a linear isomorphism. The important thing about this linear isomorphism is that conjugation on Fsn corresponds to permutation of the variables on the right. This is just obvious because conjugating a permutation by tau means applying tau to all the elements of the permutation, to all the cycles, which is exactly what happens on the right. So this is an Sn modulo isomorphism, and remember that in Sn the action is conjugation. So this is also an Sn module. Okay. Now, if you look at matrices, this is the second fundamental theorem of matrix invariance. Let me just spend a few words, which I guess everybody knows. In the work of Procesi, the trace identities came out in a natural way in invariant theory by considering the invariance of n by n matrices of size k, their sum of k by k matrices of size k, where you act with by conjugation, simultaneous conjugation with the general linear group. Now, the ring of invariance is exactly the span of all, can be thought of as the span of all the products of trace of monomials of generic matrices. So the multilinear invariants are exactly what's the multilinear invariants of degree n are exactly the denominator here, Tn intersection the identities of A. Now, the second fundamental theorem of matrix invariant tells you what are the relations among these invariants. And this is the work of Procesi. He proved that the denominator is actually in identification with the group algebra of Sn is the sum of all the two-sided ideals where the partition lambda has height greater than k. So the quotient is the sum of all the partitions of all the two-sided ideals corresponding to partitions of height less or equal to k than k. What is the character? Well, the action is conjugation. So what is the character of I lambda? Well, you have left multiplication, right multiplication, you have the diagonal action. So the character, it's easy to see. It's a chi lambda tensor chi lambda, where chi lambda is the reducible character of Sn corresponding to lambda. And here there is a problem, because you need to know how this character decomposes into reducibles, and this is not clear. Anyway, you can tell what the degree is. The degree of this character is the character of chi lambda, d lambda squared. So if you want to compute asymptotics, Regev in 81 computed this asymptotics and comes out to be constant n to this half an integer, k squared to the n, where c is a constant. Now, we said that any other trace on the matrices is a scalar multiple of the usual trace. So the question is, do you get the same asymptotics if you use another trace? Okay, remark, you can prove that if you call T sub alpha this new trace, which is a multiple of the trace of A, the asymptotics is the same, because actually the codimensions are the same. Okay. Now, what is the relation between the mixed trace identities and the pure trace identities? Well, you can go from, you take a mixed trace polynomial and becomes a pure trace polynomial by adding one extra variable and taking the trace. And this is a linear isomorphism. Why? Well, here's the reason. If you start from the right, so you have such a thing, what do? You isolate xn plus 1, and then you write f as the trace of whatever is left times xn plus 1, where g is this monomial. This is now a mixed set because it has some non-zero, some monomial which is not inside the trace. So see, this is a linear isomorphism. So the dimension of this space is the dimension of this, that is the dimension of the group algebra of Sn plus 1. So is n plus 1 factorial. Okay. But this is also an S module isomorphism. Okay. Now, what is the relation between pure trace codimensions and trace codimensions? Well, if the trace is non-degenerate, like in matrices, then you can recover from trace g n plus 1, you can recover g. So f, it will be a pure trace polynomial identity if and only if this g is a mixed trace polynomial identity. Thus, this says that the nth trace codimension is equal to the n plus 1 pure trace codimension. So if the trace is non-degenerated, you have this equality. But in general, all you can say is that the pure trace codimension is less or equal than the trace codimension. Okay. Now, let me go to polynomial identities. Let me recall something that has already been said several times. So you have the free algebra. So there is, you just erase the trace. There is no more trace. And you look at the free algebra, the multilinear polynomials and variables, and the usual codimension. And remember, there are two results that I want to point out here. One is Regev satisfies a non-trivial polynomial identity if and only if the codimensions are exponentially bounded. And then this result with Zaisev that says that the codimensions are squeezed in between two exponential functions with the same exponential base, which is called, which is an integer, and it's called the PI exponent of the algebra A. Okay. More, let me just remind you what happens in the finite dimensional case. Remember this, there is an explicit description of this number D. And I'll remind you what happens in a finite dimensional algebra. So if the field is algebraically closed, we are in characteristic 0, you write your algebra by Weber-Maltsev theorem as a maximal semi-simple subalgebra and the Jacobson radical. So these AI are simple algebras. And remember that the subalgebra, when you take a sum of this, simple summands here, which are distinct, you call this subalgebra admissible if this happens. Okay? If you multiply in some order, you get non-zero. With the Jacobson radical, eventually this could be equal to 1, so not Jacob's radical. So the exponent is the maximal dimension of an admissible subalgebra of A. That's what happens in the finite dimensional case. In the general case, there is a similar characterization using superalgebras and the Grassmann-Eberhoff. Okay. The question is, can we have analogous results for trace codimensions? So let's go to one example. You take the free algebra with trace and you mod out this polynomial, the T ideal generated by trace of X, trace of Y. Now, that means that in PTN, so pure trace polynomials, you just have one trace, right? Modulo the T ideal of trace of X, trace of Y. And sigma is an n cycle because remember that the trace of xy is equal to trace of yx. So here only to have distinct values, you have to take only n cycles. So the number of n cycles is n minus 1 factorial. So the codimensions, the pure trace codimensions are factorial. And the algebra satisfies a trace polynomial, a non-trivial trace identity. So Regev polynomial is no more valid. But maybe you might think, maybe this is because this object is too free. Maybe if it satisfies a PI, an ordinary polynomial identity, maybe it's true, the Regev theorem. Nope. Here is an example. Due to Berel, you take the algebra of infinite diagonal matrices with only finitely many non-zero entries, and you take the usual trace. This satisfies this trace identity. Well, this algebra is commutative, so satisfies the commutator x times y. So the trace of x times y times another variable. Now, this is non-trivial, but you can prove, this is Berel's result, that the basis of PTN modulo the identities is given by this, by the product of traces where you have monomials which are ordered. So the codimension you have to count on, in how many ways you can do that. That's the number of ways you can partition, you can divide a set of elements into distinct subsets. That's what's called the nth Bell number. And it's known that the Bell numbers, the sequence of Bell numbers grows over exponentially. So even in this case, the algebra is commutative, satisfies a non-trivial trace identity, but still the pure trace codimensions are over exponential. So there is no hope that Regev theorem holds. But here's the result of Berel. So you see here, since these elements are n plus 1 is a factorial, in order to have an identity, to have the codimensions to be less than n factorial, you need to have a linear combination of this that is an identity. And that's exactly the first condition in the Berel's theorem. So he proved that the pure trace codimensions are exponentially bounded if and only if A satisfies two non-trivial identities of this form. So this comes from the first example, and this is somehow related to the second example for some D. He also has a condition which is very similar, for which the trace codimensions are exponentially bounded. Okay? Okay, that's a very nice result that I wanted to mention. But let's go to the exponents. So let me take F algebraically closed, A finite dimensional algebra with trace, and let's have, this is the Wedderburn-Maltsev decomposition. These are simple algebras. This is the Jacobson radical. Okay, then like before, let's just generalize the definition of admissible subalgebra. So I take some of these simple components, distinct simple components, and I play this game. as before. I call this algebra admissible if this is non-zero. If I call it the pure trace admissible if I place only traces, no Jacob's radical. And I call it trace admissible if I have a piece with traces and a piece with the Jacob's radical. Okay? Okay, so remember these three definitions. Here's the theorem. With Ioppolo and Lamattina, if you have a unitary finite dimensional algebra with trace, let me say something that was here. I'm assuming that the trace has values in F, not in the center. Okay, here's the condition, and I assume that the trace on the Jacob's radical is 0. Then you have these two. You can find an upper bound and a lower bound on the trace codimensions and the pure trace codimensions, and that D is the maximum dimension of a trace admissible subalgebra, and that D dash is a maximum dimension of a pure trace admissible subalgebra of A. Okay, so this looks like the ordinary case. Now let me say something. There have been, after the exponent, there have been lots of papers where this term has been extended to involution, superalgebras, G-graded algebras, and some other cases. And the technique, it's always, every time you have to sweat in order to prove something, but there is you always have to find the lower bound and upper bound. Now, for the upper bound, there is a technique purely combinatorial that actually is due to Procesi, where you don't need anything. You can do it just by counting to find the upper bound. But for finding the lower bound, you always need the representation theory of the symmetric group or the general group. There is no proof that I know, as far as I know, that does not use a representation theory for finding the lower bound, except for this paper. In this paper, we cannot use the representation theory because we don't know how the tensor product of two characters of Sn decompose into reducibles. So we have to find another way. And here the way is just purely combinatorial. Okay? Okay, here's the corollary. So these two exponents exist. This is an advertising of this result. So in particular, these both sequences are either polynomial bounded or grow exponentially. Just one small remark. If you have such a trace admissible subalgebra, so means this, remember this means, then A contains a subalgebra isomorphic to this object. So this is diagonal matrix, and this is block upper triangular matrix. Okay? Block upper triangular. So you see from this, but in general, that actually you cannot compare the pure trace exponent with the ordinary exponent. Just look here. I mean, you can, this is the exponent of the algebra, is given by this part. And the pure trace exponent is given by how many components here have a non-zero trace. So you could just set this non-zero trace and here all-zero trace, and the two numbers don't talk to each other. Nevertheless, you can always say you have this inequality. These are trivial things. Okay, about these three numbers. Okay. That was the main result. And now let me give you some small things that can be proved using the exponent. Okay, some UT2 for me is a 2 by 2 upper triangular matrix with 0 trace. D2 is 2 by 2 diagonal matrices, and here for this for D2 to the T alpha beta, I mean D2 with this trace. Okay. Now here's the theorem of Ioppolo, Kotchetov, and Lamattina. They prove no restriction on the trace of J. They prove that the sequence of trace codimensions is polynomially bounded if and only if these four algebras do not belong to the variety generated by A for any choice of alpha, beta, gamma, delta. Well, you see, they prove actually that up to isomorphism, you can have only T alpha and 0, T beta beta, and T gamma delta, where gamma and delta are non-zero. Okay, that's the result. Now we prove the analogous result for pure trace codimensions. But now you remark that if you take, this is a pure trace identity for UT2. So means the pure trace codimensions are 0. So you don't need to take care of UT2. This also satisfies this pure trace identity, and the pure trace codimensions are 1. So you don't need to take care of this. So out of this 1, 2, 3, 4 algebras, you took care of 2, and here's the result. The sequence is polynomially bounded if and only if only these 2 algebras do not belong to the variety. Okay, now you can go on. Well, this remark does not follow from the result, but follows from the proof of the result. That actually, if the pure trace codimensions are polynomially bounded, then either are 0 or 1. But that comes from the proof, not from the statement. Okay. Now let me give you some more. Now here there are a bunch of results that can be proved. Something like when do the trace codimensions, the pure trace codimensions are greater than 2 or less than 2 or equal to 2? Can you characterize such algebras? Yes. And here is for if you look at 2, then you have to consider algebras that have trace exponent or pure trace exponent higher than 2, in that case 3. And so these are the algebras you find out. Well, you take 3 by 3 upper triangular matrices with this trace, and 3 by 3 diagonal matrices with this trace. And this is just the diagonal matrices with 1 corner with this trace. And then you check all this. That for these algebras, the trace exponent is 3, and the pure trace exponent here is 3, and for this is 2 by 2 matrices with trace T alpha, means alpha times the usual trace. The trace exponent and the pure trace exponent is 4. Out of this, then you can prove all these results. That the exponent, the trace exponent is greater than 2 if and only if B lies in the variety generated by A for some B that is one of these, and is exactly 2 if and only if B does not lie for all B in here, but there is at least one of these that lies in there. Okay, and then finally, the pure trace exponent is greater than 2 if only if this or this belong to this. These algebras here are what are called algebras minimal of a given exponent. So these are algebras that have a given exponent, like 3 in this case, but any proper subvariety of the variety they generate has a lower exponent. Okay, so all these algebras are of this type. Okay, so my time is over. Thank you.
Are there any questions?
I have one. In the case where the codimensions are exponentially bounded, do you know the asymptotic structure like in Berel and Regev ordinary case?
No, because it's very in the air, very airy. I mean, we know a condition for which they are exponentially bounded. You're talking about when they are exponentially bounded.
Yes. But because you have this result with maybe different polynomial powers.
But look, let's look at the two polynomials. Where are they? Okay. You see the first polynomial, if your algebra satisfies a standard identity, satisfies a multilinear polynomial of degree d, then it satisfies the first one, right? Because you just take the trace and multiply by one variable. So the first, if your algebra satisfies a multilinear polynomial of degree d, that means nothing, right? And the second condition is very strange. I mean, it's very hard to understand how is an algebra that satisfies these two identities. Well, of course, you don't know the algebra, you have to work inside the theory. The theory generated by these two. I have no idea. But it's, of course, it's very interesting.
Okay. Any other questions?
Let me say just one more thing. A trace is you need some natural traces to work with, like matrices, like even for finite dimensional algebras. When our results are for when the trace on the Jacob's radical is 0. But if the trace on the Jacob's radical is non-zero, you can have some very wild phenomenon. And I don't know how much interesting this can be. That's the main obstacle here. Try to prove results that are nice, that make sense. They have lots of examples.
Okay. So who else wants to ask a question?
Okay, the second identity is something like Capelli-like identity when you have here. When you have fixed variables, x1, xd, and you have some y's. But this is simply something which is some inspiration. And I don't know whether there is some reason for this. And do you have some idea about the trace exponent or pure trace exponent? Something in the spirit of your theorem of Misha Zaitsev for the usual minimal varieties of with respect to the usual coordinations.
Yes. I have no idea, but for finite dimensional algebras, it makes sense to search for. Of course, I didn't think about this, but I think it's reasonable, it's doable, but in the setting of finite dimensional algebras, because for infinite dimensional algebras, I don't know. What is a trace on the Grassmann algebra, for instance? It's,
yeah, there could be very many traces.
Right.
Okay. Other questions, please?
I don't know.
If not, let us thank Antonio once again.
Thank you.
It's a pleasure to introduce to Professor Mikhail Kotchetov from Memorial University of Newfoundland. He will be speaking about grading on real simple algebras. Am I right? Yeah, fine grading on classical simple real algebras. So, Professor Kotchetov is the deputy director of Atlantic Algebra Center, again with very close connections with Vesselin. So it's a pleasure for me to introduce him for his talk. Please.
Right. Thank you to organizers for the opportunity to speak at this distinguished event. So as announced, I'm going to speak about gradings on simple Lie algebras, and today I decided to focus on the case of real Lie algebras, although I will say something about complex as well, or more generally over any algebraically closed field, and real could mean over real numbers or over any real closed field more generally. Nothing that I will say will use the topology of real numbers. All right, so here is a brief plan. First, I will introduce some definitions and examples. Well, everybody knows what a grading is, but there are some less well-known concepts like refinement, coarsening, universal group. I will go through that. First, that will be the first part. And then I will discuss some, well, examples, A1, G2, and then I will translate the problem from classical simple Lie algebras to associative algebras with involution. And the final part of the talk will be about about the associative case, which can be translated back to Lie algebras. So this is the plan. All right, first of all, definition of a grading. So perhaps I will give you a slightly more general one than what you normally see, because here we are indexing components. So these vector subspaces in my algebra A that form this direct sum decomposition, they're indexed in most general case by a set, not necessarily a group. And we insist that whenever the product of two such subspaces is not zero, it is contained in a third subspace. And that defines a partial operation on this set, indexing set. So if X and Y have the property that component labeled by X and component labeled by Y, the product is not zero, then this operation X star Y is defined, and the result is this unique Z, so that the component labeled by Z contains the product AX AY. All right, so as I said, more familiar situation is when we have a group, or more generally semi-group, which will be writing multiplicatively. And here we insist that when we multiply subspace or component labeled by G with one labeled by H, we land on the component labeled by G times H. So this is the operation in my group or semi-group. And if such G grading is fixed, so the pair algebra with the grading is said to be a G-graded algebra. And A sub G is, as I already mentioned, a homogeneous component. G then is called the degree of that component. So here we can take for algebra also more general concept of an algebra. Here I defined for the standard situation where we have product that takes two variables, but we can have any number of multilinear operations. We just have to modify this condition or this condition to putting the appropriate number of components and applying the operation to that. So it has an obvious generalization to universal algebra. Okay, and if we have a grading in this general sense in the first definition, it may be possible to realize as a group grading or semi-group grading, by which we mean that there exists an embedding of this indexing set S into some group or semi-group, so that this embedding preserves this operation. So when this partially defined, when this operation star is defined, it corresponds to the product in the group or semi-group. We can even think that this set S is a subset of this group or semi-group. Okay, and here are some examples. If we take the matrix algebra M and F, take matrix units, span one-dimensional subspaces by each of them. That's a direct sum decomposition, which is a semi-group grading, but it's easy to see that it's not a group grading. So it cannot be realized as a grading of a group. To make it a group grading, we have to put together all of the matrix units that are on the main diagonal and form a single component out of them. And the remaining components are still one-dimensional. And this can be, in fact, realized as a grading by an abelian group. So this is a root space grading in Lie algebra. Simplest example. Okay, and the support of a grading is the set of all the labels of non-zero components. And in general, it's going to be a subset of our group or semi-group, not necessarily closed under the operation. But an interesting fact is that if we're dealing with simple Lie algebras, which I will be doing in this talk, then in fact, the support always generates an abelian group. If it was a semi-group grading, it actually can be realized as a grading of an abelian group. So if we're talking about simple Lie algebras, then semi-group gradings, group gradings, or abelian group gradings, they're all synonymous. And there was a long-standing question if there exist non-semi-group, sort of non-associative, so to speak, gradings on simple Lie algebras. And this was just very recently, 2 months ago, answered by El Duque. So there are indeed such gradings, and the smallest example that he constructed is SO26. And I believe he will be talking about this example and its connections to other topics in his talk on Friday. Okay, and now if we can realize a grading, so from now on I will be focusing on group gradings. So if a general grading can be realized as a group grading, in principle there are many groups over which it can be realized, but there is a universal construction here. So we just take the support as a set of generators of the group, and we impose relations of this kind. So whenever component labeled by X times component labeled by Y is not zero and contained in component labeled by Z, then XY should be equal to Z in our group. Or in other words, XY equals this X star Y, the partially defined operation from the previous slide. So this group presented in this way is called the universal grading group. And if our grading can be realized over an abelian group, we can do the same and take the abelian group with that generating set and the same relation. So that will be universal abelian group. And again, if we're talking about simple Lie algebras, this will be the same thing. Okay, and then every grading that can be realized as a group grading can be realized over its universal group. So this mapping of set in the group, in principle, it may not be injective because of the relations, but injectivity is precisely equivalent to the possibility of realizing our grading as a group grading or abelian group grading. So this is a sort of the most important realization. All right, so an example, a very easy example, take SL2, the standard basis of it. This will be a grading in our more general sense. And to realize that over a group, we can just label them -1, 0, 1. That will be a Z grading. Or we could consider this -1, 0, and 1 not as integers, but integers modulo M. -1 should not be 1 modulo M, so M greater than 2. The universal group will be this infinite cyclic group Z, although it can be realized over finite cyclic groups as well. And this is an example, of course, of the more general situation, root space decomposition of a semi-simple Lie algebra. It can be viewed as a grading by free abelian group, namely the root lattice. And the support of this grading is the zero and the root system. Components are almost all one-dimensional, except the zeroth component, which has dimension R, the rank of this semi-simple Lie algebra. So very well-known thing. Now let's look at a grading that is not of this sort. Again, SL2 is the simplest example. We can take the so-called Pauli matrices from physics and then span again one-dimensional subspaces by them. That will be a grading. And to make it a group grading, we'll label these components by A, B, and C, which are the non-trivial elements of the Klein four group, so Z2 squared. So that will be Z2 square grading on SL2. Well, we can also take this as a grading on the matrix algebra, associative matrix algebra. So there will be an extra element then in the support because the identity matrix will span component labeled by E. All right, and generalization to n by n matrices. So again, we can take it for associative algebra of all matrices, or take it as a Lie algebra, or take traceless matrices inside. That will be a graded subalgebra. So we get Zn gradings on all of these, provided our ground field contains a primitive nth root of unity. Then we take these two matrices. Sometimes they're called generalized Pauli matrices in papers written by physicists, but as Yuri Bakhturin tells me, this actually is well known from much longer ago. These are Sylvester's clock and shift matrices. So one of them is consecutive powers of this root of unity on the main diagonal, so this diagonal matrix called clock, and the other one is the cyclic shift of standard basis vectors. So these matrices commute up to this factor epsilon, this primitive root, and the nth power of x is identity, nth power of y is identity. So the monomials in x and y, like this, x to the I, y to the j, where I and j run from 0 to n minus 1. This will be a basis of the matrix algebra, and if I span one-dimensional components and label them by elements of Zn cross Zn, in this way, that gives me a grading. Okay, so if we have a grading by group G, then we can produce a lot of other gradings using group homomorphisms from G to any other group. So if we have a grading gamma by group G and any homomorphism from G to H, we can put together all of the components AG, where G runs through the set of inverse images, pre-images of this fixed H. And that will be component labeled by H. And that is very easy to check. This is again a grading. So it's induced by this group homomorphism. This is a very well-known situation, in fact. So if you think of polynomials and then variables, you can define a grading on that by any abelian group by deciding what the weight of each variable is. So for each variable, you assign an element of your abelian group. And then for a monomial like this, we just take the corresponding element of this abelian group. Usually this is written as a sum, but as I said, I'm writing groups multiplicatively, so it looks like a product. So this will be an example of this construction. So from the standard multi-degree Zn grading, we take homomorphism from this free abelian group to the group H, sending the ith standard basis element of Z to the n to this weight that we assign to variable xi. And then this homomorphism gives us precisely this grading determined by the weights of the variables. Well, we can also look at an example of Lie algebras. So SL2, let's take again the simplest example. Then the Cartan grading that we started with. Remember, we said that we can take labels modulo m greater than 2 will have the same grading. But if m is equal to 2, what happens then, this first and last component come together in a sum like this, because they're mapped to the same element of Z2. And so the induced grading will be this one. And in fact, if the field is algebraically closed, you don't really get anything else for gradings on SL2. It will be a Cartan grading or Pauli grading or this coarsening, and of course the trivial grading. And so in particular, if I take Pauli grading Z2 squared and take any homomorphism to Z2, it will give me a Z2 grading, which will be isomorphic to this one above. I will define in a moment what I mean by isomorphic. Okay, and if the field is not algebraically closed, so my interest in this talk is real numbers, so then we have something more complicated. So they're depending on the on which homomorphism we take into Z2, you get either isomorphic to this one or not. So over non-algebraically closed fields, the situation is more complicated, even for SL2. Okay, so I already said the word coarsening. The formal definition is here. So if you have two gradings on the same algebra, gamma and gamma prime is a coarsening of gamma if every homogeneous component with respect to gamma is contained in some homogeneous component with respect to gamma prime. And since both are direct sums equal to A, this means that every component of the gamma prime grading is in fact direct sum of certain components of the grading gamma. And if we have proper inclusion or direct sum of more than one summand in at least one instance, we say this is a proper refinement or proper coarsening, and grading is fine if it does not have proper refinement. Okay, so here's an example that we just had on the previous slide. This is a proper coarsening of Cartan grading and also of the Pauli grading. Now, injective, it will not be proper. But here's an example. In matrices, we have this. This actually is a fine grading. Well, it does admit a refinement if you take each matrix unit separately, but that is not a group grading. So the fine is relative to a class of gradings. So here I'm working with group gradings only. So this kind of refinement doesn't count. All right, so homomorphisms of graded algebras. Well, everybody knows what that is. If you have two algebras graded by the same group, then homomorphism of graded algebras is a homomorphism of algebras that maps a component of the first grading to the corresponding component of the second, so with the same label. And in particular, we can talk about isomorphism of graded algebras and graded isomorphic algebras. Now, there is another concept where we allow algebras graded not necessarily by the same group. So let's say on algebra A, we have a G grading like this, and on A prime, we have an H grading by some other group. Then these gradings are equivalent if there is an algebra isomorphism, which maps components of the first grading to components of the second, but here the components can be relabeled by some bijection between the two supports. And again, this can be done nicely using group isomorphisms if we use universal groups. So if these G and H are universal groups of these gradings, then this bijection alpha actually extends to group isomorphism, and this condition then relabeling can be restated in this way, that it's an isomorphism of graded H algebras where A is graded by H using this homomorphism, right? It's a homomorphism from G to H, so it induces from a grading gamma some H grading, which we denoted like this, and then, well, with respect to this H grading, A is isomorphic to A prime with its own H grading. So this is the equivalence relations up to which we classify graded algebras. Or if we have the same algebra, we can consider different gradings on it up to isomorphism or up to equivalence. And well, it turns out that for many nice or important algebras, you can actually classify all gradings up to isomorphism group gradings or abelian group gradings, and all fine group gradings up to equivalence. So in this talk, I will focus on the fine case. The answers are a little simpler. All right, and these two classifications are really not, they are related, but they're not easily translatable from one to the other. So here I try to explain the reasons, but we're short on time, so let's just move on. All right, so final piece of preliminaries is a transfer theorem. So if we have two finite dimensional algebras, and they can be with any number of multilinear operations, they don't have to have the same type of operations. So then if we have a homomorphism of these algebraic group schemes, well, if you don't know what this is, you can think of characteristic 0 algebraically closed field, then this will be just the algebraic groups of automorphisms, but over an arbitrary field you have to take affine schemes of automorphisms. Anyway, if we have a homomorphism of these groups or affine group schemes, we can move. So for any grading on A, we can produce a grading on B, and isomorphic gradings go to isomorphic gradings. And this procedure actually commutes with the procedure of inducing a grading with a group homomorphism from the grading group to another group. So we get a corollary that if this theta is an isomorphism of the automorphism groups, then this transfer actually gives bijection. So we have the same classification of gradings on A and B up to isomorphism, or of fine gradings up to equivalence. Okay, so here is an example of how it works. Lie algebra A1. So gradings on A1, so SL2 that is, they are the same as gradings on quaternion associative algebras. So here, well, any so as I said, SL2 over algebraically closed field, it's SL2. If the field is not algebraically closed, there are twisted forms of this. But anyway, any such can be realized as the commutator algebra inside quaternion algebra. And the restriction map for automorphisms is actually an isomorphism of the groups or group schemes. And so we can translate back and forth. And to classify gradings on quaternions is rather easy. So over the real numbers, we have SL2 and SO3 are the, or if you like, this is SL1 of quaternions. So these are the forms of type A1, and they correspond to the split quaternions, that is to say 2 by 2 matrices, and the division algebra of quaternions. And we have the translation of gradings back and forth. So on SL2R, on the split form, we have 2 fine gradings, which I already displayed at the beginning of the talk. And on SO3, there is only one, namely the Pauli grading. And from these fine gradings, you can produce all other gradings. So that's what the classification of all G gradings up to isomorphism looks like. So we can just, for any group G, and select an element G in it and define a grading like this. And these 2 such gradings will be isomorphic under this condition. And the remaining gradings that are not of this form, they correspond to the Pauli matrices. And so here is a classification up to isomorphism for them as well. So the real numbers, it's a little bit more involved than of algebraically closed field. So there are some characters of group Z2 or Z2 square appear. Okay, so the same game we can play with G2. Well, this is not classical, but I included in this talk. So everything goes in the same way, except instead of quaternions, we have to use octonions. And instead of the derived subalgebra, we take the derivation, algebra of derivations. And then Alduke classified already long ago the gradings on octonions, and well, he described them in this theorem, and then you can classify them up to isomorphism. And in particular, over field of real numbers, you have two fine gradings on split octonions or split G2 with these universal groups Z squared and Z2 cubed. So this is related to the Kelly-Dixon doubling, done 3 times. It gives you Z2 cube grading. And only one for the compact G2, namely this double coming from the Kelly-Dixon doubling. All right. So now the main characters of this talk. So this classical ABCD. So we already discussed A1. So here it will be A2 or higher. So then what do we have? We can realize this classical Lie algebras as skew elements in associative algebras with respect to an involution. We have to choose the right type of involution. Sometimes we have to take derived algebra and characteristic P, also quotient by the center. But this is all well known, so I don't go in detail through this. But the point is that when you use these standard realizations, there is a homomorphism from the automorphism group of the associative algebra with involution to the automorphism group of the corresponding Lie algebra. It's simply a restriction, or maybe a restriction modulo the center if there is a center in series A. And this restriction homomorphism is actually an isomorphism, except in case D4. So and here we just for BCD we just take central simple associative algebra with an involution. For type A, we need algebras with involution that are not simple as algebras. So the center will be an extension of degree 2 of our ground field. So either split extension or a field extension. And we must take involution of the second kind, so it's not trivial on this center. So this then gives us realization of all Lie algebras of type AR. And the restriction map also, except in case A1, which we already discussed, it turns out to be an isomorphism. Again, there is an exception in characteristic 3, but that one can be handled using octonions. So this is the translation to the associative case. So now I can just focus on these associative algebras, which are central simple as algebras with involution. So not necessarily central simple as algebras, but as algebras with involution. Okay. So there is this important result about gradings on associative algebras, so graded version of Wedderburn theorem. So graded division algebra is graded algebra where every non-zero homogeneous element is invertible, and it plays a similar role in this graded version to the role played by division algebras in the standard one. So if we have a G-graded algebra, associative, and if it's graded simple and satisfies the same Ding chain condition on graded one-sided ideals, then it can be realized as matrices over graded division algebra, or in more abstract terms, endomorphisms of D module and D module of finite rank. So graded modules over graded division algebras are necessarily free. So they, in fact, admit a basis consisting of homogeneous elements. So this endomorphism ring is actually matrices. And this is actually if and only if here. The converse is also true. So how do we define grading on the endomorphisms? Well, an endomorphism is said to have degree G if it maps elements in the module that have degree h to elements that have degree gh. So it gives this shift of grading. Well, on the left, if the group is non-abelian, we need to keep track. And then you take the sum of all such. So in general, this will be something called the n-gr, right? It's not the whole thing, but if we have these finite rank modules, it's actually the whole thing. And we can, as I already said, represent things in the language of matrices. If we fix a basis consisting of homogeneous elements, these are their degrees, then we can, so this endomorphism algebra is isomorphic to matrices over D, or it's slightly more convenient here for me to write it as this tensor product, matrices over F tensor D. And then to this element, matrix unit tensor and element of D, I assign this degree. And this agrees, of course, with this rule above for endomorphisms. All right, so in particular, all of this applies to matrix algebras over F, because whatever grading we put on them, these conditions in the theorem will be satisfied. But then here we can say more. The D itself has to be a matrix algebra of the size being divisor of N. And if F is algebraically closed, then the identity component of this D is an ordinary division algebra. So it has to be the ground field, which means that all homogeneous components in D are one-dimensional. So we have this decomposition of matrix algebra with a grading into tensor product of two pieces. And here we have what's called an elementary grading. So matrix units are homogeneous elements. And here we have this, what we call division grading. So it makes it into a graded division algebra with all components being of dimension 1. So this is a result of Bakhturin, Segala, Zaitsev, and that is already quite a while ago, but plays very important role in this theory of graded algebras. All right, so coming to fine gradings, coming closer to fine gradings. So this division algebra that we mentioned, the structure of them over arbitrary fields is not so simple, but over algebraically closed field. And also I will be assuming that my grading group is abelian. That's another simplifying assumption because I'm interested in Lie algebras. So in that case, the D will simply be tensor product of matrix algebras. Each has its own grading, this by clock and shift. Yeah, so as described before. Okay, and more generally, if the field is not algebraically closed, but still assuming that the identity component is the ground field, so all components in D one-dimensional, that means that D becomes a twisted group algebra. And we can describe it using alternating bicharacters. So if we pick a non-zero element in each component, so component labeled by T spanned by element xt, then this equation defines as a scalar, right? Recall T is assumed abelian, so left-hand side and right-hand side have the same degree, so they differ by scalar. This scalar is easily seen to be an alternating bicharacter, so it's a multiplicative in each variable and has this property. So by analogy with linear algebra, we can define the radical or kernel of this beta in the usual way. So it's equal to 1, right? Not 0, because everything is multiplicative. And D will be central simple if and only if beta is non-degenerate. So radical is trivial. Okay, so central simple graded division algebras. If beta is non-degenerate, then we can construct a symplectic basis. So again, this is by analogy with linear algebra. So consisting of pairs, so that corresponding elements pair non-trivially. So it's a primitive root of unity that has degree equal to the orders of these two paired elements. And if you take elements that are not paired with each other, you always get 1. So that's a symplectic basis. And then you can present your algebra, graded algebra, in this way. So we recognize that we can write it as a tensor product of this so-called symbol or cyclic algebras graded by product of two copies of cyclic group. Yeah, so each of them has its own copy. Okay, and if we are talking about real numbers, then of course all primitive roots of unity will have degree at most 2, so T will be elementary 2 group. And well, the classification is known over the reals, so independently done in 2 papers. And here now we will have to look at anti-automorphisms, or well, we are interested in involutions, right? So we now understand what the algebra looks like. It's NDV from that graded Wedderburn theorem. We understand what D looks like. Now we need to understand the involutions, or more generally anti-automorphisms on this. And Luque proved that any anti-automorphism is actually coming from a sesquilinear form. So any anti-automorphism of NDV as a graded algebra. So here's what it means. And this sesquilinear form is not uniquely determined, but it's very easy to check when 2 of them define the same anti-automorphism. And here I have more fresh results. So this is a joint work with Alberto El Duque and Adriano Rodrigo Escudero. So if we want this anti-automorphism to be an involution, then actually this sesquilinear form can be chosen Hermitian or skew Hermitian. And it's not unique. And again, we can understand when 2 such things determine the same involution. So all of this is, of course, very well known without a grading. So these are graded versions of classical results. Okay, so right. So if we, in particular, if we have an algebra which is central simple as an algebra with involution, then whatever grading we put on it, it can be written as NDV for some D and V, and then this D must, if we want R to admit an involution, then this D must also admit an involution. That's from here, right? This is the involution with respect to B was a Hermitian or skew Hermitian form. All right, so I'm almost out of time, so I have to define these fine gradings. So what we do here? So we have matrices over this graded division algebra. The group is abelian, so here we can write in any way we want. So you saw this formula already before. I have tildes over GI, GJ because now we take them sort of free. They are a basis in the free abelian group. And the total group will be this free abelian group cross T, the support of the division part. And then this will be a graded algebra. I can double it. So the opposite will still be graded because my group is abelian. And then we have exchange involution. So we get an algebra which is central simple as an algebra with involution, if D was central simple. And in the other case, when it's not this direct product of algebra and the opposite, there are more parameters, and and the grading group is more complicated. So we still have K by K matrices over D, but the degrees, this G1 through GK that we attach to basis elements of the module over D, they are no longer a free basis in an free abelian group. We have to impose relations like this. And then this matrix gives Hermitian or skew Hermitian form which defines an involution that's degree preserving. So these conditions above are precisely what is necessary and sufficient to what is necessary. Yeah, sorry, necessary and sufficient to make it degree preserving. Okay, so let me quickly finish. Can I have a couple of minutes to finish? Oh, okay.
Couple.
All right. So, and if we have an involution on an Artinian algebra, and which is simple as an algebra with involution, then for every G grading, we can obtain from one of these constructions using a homomorphism from those groups that are sort of as free as possible to keep this involution degree preserving into a group G. So for any G grading, they can be realized in this way. Oops, and all right. Then we can decide which of these are fine. So they indeed turn out to be fine. In most cases, there are some exceptions. If the grading on D is fine, which is the case, for instance, if all components are one-dimensional, then the grading on this matrices will be fine grading on it as algebra with involution. And well, here is a classification in the central simple case when R itself is central simple, not central simple algebra with involution. So, I guess this is a bit too much to read, but anyway, this is a very explicit description, and we can tell when two such things are equivalent. So let me skip to the last slide. So here I explain that not only do we have this alternating bicharacter, we also have something like a quadratic form. So involutions are associated to quadratic forms. And on the abelian group, on the support. And also in the real case, quadratic forms are associated with squaring. If we have a elementary two-group grading group, then the square of every element will be a scalar, which is positive or negative. So you get another quadratic form in this way. And if you use it to define involution, this is something called distinguished involution in the real case. In the algebraically closed case, there are no distinguished involutions, so we have to take all quadratic forms, which have this polarization beta, the alternating bicharacter associated to our graded division algebra. So these quadratic forms, they are in bijection with T, but not in a canonical way. So you have to pick a base point, and then you can, so one of these quadratic forms, and then you have a bijection with T. And here is the last slide. So then the classification of fine gradings up to equivalence. So these are the different cases that arise. So here we have central simple as an algebra with involution. So the center could be the ground field or this direct product of two copies or extension of degree 2, field extension. And F could be real closed or algebraically closed. And the gradings will be classified by T, and also in most cases by a multiset sitting inside some vector space over the field of two elements. So in the simplest case, here, the central simple case, center is the ground field. For the real field, we have multisets in this elementary two-group T itself, under the action of the orthogonal group with respect to this quadratic form associated to D, coming from squaring. So square is positive or negative scalar. And in the algebraically closed field, here we have these quadratic forms, which is in bijection with T, but not canonically. And the group that acts on these multisets in this set is the symplectic group. And other classical groups over the field of two elements also appear in this picture. And since this is a conference in combinatorics, let me finish with one last combinatorial result. we can count the number of fine gradings. We did this in the algebraically closed field. Here, the number will depend on divisibility, because the size of this group T has to be a divisor of dimension. So its behavior will be irregular. So to get something regular, you need to average. But after averaging, the number of fine gradings grows in this intermediate way. It's bounded on two sides by exponential, but to the k to the power of 2/3. All right, this is it. I stopped. Thank you.
Thank you very much. So we are over time. So if we have some quick questions, please ask.
I'm sorry, can I ask?
Sorry, you have a question?
Yeah, that's in respect with the last result that you mentioned, this combinatorial result. Do you know with what this power to divide by 3 appears?
Sorry, which result?
The last one.
This is the last combinatorial.
Here.
Yeah.
So the question is what?
Where this degree, from where this degree to divided by 3 appears? What is the reason?
Well, I can't really explain reason. You have to count the number of multisets, and well, that's with partitions. You can count, and counting orbits is complicated. So we just have very rough estimates. That's why we don't have a precise asymptotic here. We just have rough estimates. Basically, the orbits, sort of size of the orbit is estimated between 1 and the size of the group. So something like this. So it's not very precise counting. So mostly it boils down to counting multisets, and the group sort of plays a secondary role there. You can prove that it doesn't matter very much for the asymptotic behavior, at least if you're looking for rough estimates like we did.
Other question?
I have a question. I'm Vladimir Gergikov from Sofia. I'm using gradings which are generated by finite order automorphisms on simple Lie algebras. Now, do you have refinements for such gradings? I mean,
so the ones associated to a single automorphism, those will be gradings by a cyclic group, well, finite or infinite, and those were classified a long time ago by Katz. But yes, some of them can be refined. So you can split each component into pieces by introducing another cyclic factor in your grading group. Or if you think in terms of automorphisms, you have 2 commuting automorphisms of finite order, let's say. And yes, you can compute. You have to, if you want to take a second automorphism, you take the centralizer of the first one, and you're looking for an element of finite order. So there are such computations done, but I mean,
any reference?
I don't know if I answered your question.
Yeah, okay.
So we don't do it this way in this work. We translate to the associative case and get them all at once. But another approach, which is necessary or for the E-types, let's say, that don't have these associative models or even alternative models, there you pretty much have to work with automorphisms directly, and then you're doing computations in the automorphism group, such as computing centralizers. And there are many papers like this. Well, I can give you some references if you are interested.
Okay. Yeah. Okay, we are going over time. So if there is a really quick question, please ask. No, thank you very much again, Mikhail. So let's thank the speaker again.
So the next talk will be by Diogo Diniz. He will speak on the number of gradings on matrix algebras.
Okay, so first of all, I'd like to thank the organizers for the opportunity to speak here. So this is the outline of the talk. I'll briefly recall some results on graded algebras, which were already defined, and then present some results on the gradings on algebra of upper triangular matrices and on matrix algebras, and also on block triangular matrix algebras. And then the main topic and results I want to show is in the sections titled Counting Gradings. So as was already defined, here we'll take G to be a group, A an algebra of a field F. So a grading by G on A will be just a decomposition like this of A as a direct sum of subspaces, such that these inclusions hold for every G and H in the group. So we call these subspaces the homogeneous components of the gradings. This was already mentioned. The simplest example you can take is take any algebra A, any group G with neutral element E. So we have the natural decomposition in which the subspace indexed by E is the whole algebra A, and the remaining subspaces are all zero. So this is called the trivial grading. If you take A to be the algebra of 2 by 2 matrices over F, so we can decompose A as a direct sum of A0 and A1, where A0 is the subspace of diagonal matrices, and A1 is the subspace here, and this is a Z2 grading on A. Another grading on the same algebra, here we assume that the field is of characteristic different from 2, is obtained by means of the Sylvester matrices, which were already mentioned. A, B, and C here, we have A squared is equal to B squared is equal to the identity matrix, and AB is equal to C is equal to minus BA. And therefore, we obtain a Z2 times Z2 grading on the matrix algebra, in which the homogeneous components are these 4 subspaces given here. So in general, we pose the following problem given in algebra A to describe all group gradings on A. So for M2F, without restrictions on the field, this was done by Casal, Bobok, and Pascalescu. Valenti and Zaitsev classified the group gradings on the algebra of upper triangular matrices over an arbitrary field F. Baturin and Zaitsev describe the group gradings on matrix algebra, where F is the field F is algebraically closed, and gradings on block triangular matrix algebras were classified by Valenti and Zaitsev and also by Yukihiti. We're going to mention these results later on. So if you take the algebra of n by m matrices over a field F, we can define the elementary gradings in the following way. Here, Eij is the usual elementary matrix with 1 in the ijth position and 0 elsewhere. So we take an M tuple G1 to Gm of elements of the group, and we decompose the algebra of m by m matrices like this. A is the direct sum of the subspaces AG, where AG is the subspace spanned by the elementary matrices Eij, such that Gi Gj minus 1 is equal to G. So this is a grading called the elementary grading induced by G. We defined the elementary gradings on the algebra of upper triangular matrices in the same way, and more generally on subalgebras of MMF that are generated by elementary matrices. We also recall the polygradings, which were already defined. So we take A to be the algebra of m by m matrices, take this matrices A and B here, and they satisfy the relations AM is equal to B, M is equal to the identity matrix, and AB is equal to epsilon BA. And hence we obtain Zm times Zm grading on the algebra of M by M matrices if the component indexed by the ij is the subspace spanned by the matrix AI Bj. So, okay, let us see what results we have for upper triangular matrices. First, we recall that the graded algebras A and B are isomorphic as graded algebras if there exists an isomorphism of algebras phi from A to B, such that phi of AH is equal to phi of AG is equal to BG for every G in the group. So the result by Valenti and Zaitsev is that if you have G an arbitrary group and F a field, then every G grading on UTMF is isomorphic to an elementary grading. So more precisely, if you take A is equal to the algebra UTMF, and this is the composition here, A is the direct sum of the subspaces AG, this is a G grading on A, then A as a G graded algebra is isomorphic to UTMF with an elementary G grading. So in particular, if we have G a finite group, then we can count the elementary gradings on these algebras, and Di Vincenzo, Kushlukov, and Valenti did so in 2004. So if you take G a finite group, then the number of different elementary G gradings on UTMF is the order of G to M minus 1. And they also prove that any two different elementary gradings satisfy different graded polynomial identities. So in particular, the number of non-isomorphic elementary G gradings on UTMF is the order of G to M minus 1. And this is the type of result we want to present here. This is our main goal. So now we move on to the gradings on matrix algebras, and they're classified in terms of two types of grading. This was already mentioned, the division gradings and the elementary gradings, which we already mentioned. So the division gradings are presented here. Take T to be a finite abelian group, F an algebraically closed field. So we have a division grading on MMF with support T that makes the algebra a graded division algebra. If and only if the characteristic of the field does not divide M and T is isomorphic to this group here. And this indexes L1 to LR are such that the product of L1 to LR is equal to M. And moreover, the isomorphism classes of these gradings are in one-to-one correspondence with the non-degenerate alternating bicharacters of the group T. So these are the division gradings. And there is this construction that allows us to combine a graded algebra to construct a grading on the tensor product of any graded algebra with the algebra of M by M matrices with an elementary grading, which is called induced grading on the tensor products. And this goes as follows. We take A to be a G-graded algebra, and B, the algebra MMF with the elementary grading determined by the tuple G1 to GM. And we consider the algebra R, the tensor product of A and B. So this has a G grading, which is R is the direct sum of the subspaces RG, where RG is the subspace spanned by the elements of the form A tensor EIJ, where A lies in the component AH, and I and J are such that GIH GJ minus 1 is equal to G. So in this way, we obtain a grading on the tensor product of A and B that is called induced grading on the tensor product. And then we can combine division gradings on matrix algebras with elementary gradings to construct new gradings on other matrix algebras. And the result by Bahuri and Zaitsev is essentially that any grading on a matrix algebra can be constructed in this way. So more precisely, you take MMF, let A be this algebra with a grading here. A is the direct sum of the subspaces AG. Here G is a group and F is an algebraically closed field. So in this case, the number M can be decomposed as the product of P and Q. There exists a subgroup H of G of order P squared, Q tuple G1 to GQ of elements of G, and MMF is isomorphic as a G-graded algebra to the tensor product MPF tensor MQF, where MPF has a division grading with support H, and MQF has the elementary grading determined by the tuple G. So this is how we obtain the gradings on MMF. Now, a similar description occurs for the so-called block triangular matrix algebras. So now we need M and S tuple of positive integers, and let N be the sum of the entries of the tuple M. So we associate to this S tuple M here an algebra, which we denote by UTM, which is called the algebra of upper block triangular matrices. And this is just the subalgebra of M and F that consists of the matrices of this form here. So we have A11, A12, etc. And the Aij here is a block of size Mi times Mj. So the results we have on the gradings on these algebras are the following. So Valenti and Zaitsev did classify the gradings by finite abelian groups on these algebras over an algebraically closed field of characteristic 0. Yukihide proved that the result of Valenti and Zaitsev holds for an arbitrary group and a field that either has characteristic 0 or large enough. And the classification that they obtained is analogous to the classification by Bakhturin and Zaitsev for matrix algebras. And also, Yukihide and Kotchetov classified up to isomorphism the gradings by an abelian group on these algebras, on this block triangular matrix algebras, over an algebraically closed field. So the result we like to mention is this one. So let G be any group and be an S tuple of positive integers, and consider a G grading on the algebra A, which is the algebra UTM of upper block triangular matrices over a field F. And the hypothesis on the field is that the characteristic of F is 0, or the characteristic of F is greater than the dimension of A. So in this case, we have a division grading, In this case, we have a division G grading D on some matrix algebra, M and F, and also an algebra B, which is some upper block triangular matrix algebra UTN. Here N is an S tuple of positive integers, and B has some elementary grading. So there exists this division grading D and this elementary grading on a block triangular matrix algebra B, such that A is isomorphic to the tensor product of D and B. So these are the results on the classification of gradings on matrix algebras and on upper block triangular matrix algebras that we need. And the type of results that we want to describe is to count the isomorphism classes of the, first, mostly the elementary gradings on these algebras by a group. So first, we want to present the result of Bobok and Dascalescu. They counted the elementary gradings on MMF for the group G, which is ZPN. Here P is a prime number, N is a natural number. And well, in order to present their result, we need to define some notation. So we need to define these numbers S and T here, and this number, these numbers gamma T here. So let S and T denote the number of subgroups of order PT of the group G. So they prove that for T going from 1 to N, the number S and T is given by this formula here, so you can just count it. And we define the gamma T for T going from 0 to N in the following way. So we set gamma T to be 0 if the P to N minus T does not divide M. And well, we define it now in case Pn minus T divides M. So first set gamma 0 equal to 1 if P to N divides M. And for any T between 1 and N such that P to N minus T divides M, we set gamma T to be the number given by this formula here. So this binomial coefficient here minus this these numbers here. So now that we have defined the S and T and the gamma T, we can present the result of Bobok and Daskalescu. Now, the number of isomorphism types of good gradings on MMF is given by this formula here, 1 over PT times gamma T times S N minus T, T going from 0 to N. So this is the result, and in particular, you can take N to be 1, and the number of isomorphism types of elementary ZP gradings on MMF will be this, given explicitly by this if P divides M, and by this if P does not divide M. So this is the type of result that we were interested in. On this line, we'd like to mention that, for example, this was already mentioned in the previous talk, Kotchetov, Parsons, and Sadov, they determined the number of equivalence classes of fine gradings on matrix algebras and on classical symbol algebras over an algebraically closed field. Characteristic is not 2 in the Lie case. Di Vincenzo and Nardoza, they studied graded identities in verbally prime algebras. And for instance, they were able to prove this equivalence here just using graded identities. So they considered certain ZP plus Q times Z2 gradings on this verbally prime algebras and PQE that are obtained by combining elementary ZP plus Q gradings on the matrix algebras and the canonical Z2 grading on E. And they were also able to determine the number of isomorphism classes of such gradings on MPQE. And analogous results were obtained by Fidelis, myself, Bernardo, and Kushilukov for certain G times Z2 gradings on MPQE, or G is a finite group. So we described the gradings on matrix algebras and on block triangular matrix algebras. We know how to construct them. Now we need to determine when two such constructions are isomorphic. So the result we need is this. This is done here. So let M and M prime be tuples of positive integers. G and G prime be tuples of elements of the group of the appropriate sizes. And let B and B prime be the algebras UTM and UTM prime with the elementary gradings determined by G and G prime respectively. And also let D and D prime be G-graded algebras with a division grading. So the G-graded algebras, the tensor product of D and B, and the tensor product of D prime and B prime will be isomorphic if and only if M is equal to M prime, and we can find the G in the group such that this algebra here is isomorphic to D prime. And moreover, there exists H1 to Hn in the support of D and a permutation sigma such that this equalities here, G I prime is equal to G sigma I, H sigma Ig, hold for I from 1 to N. So finally, we need some more notation, which is borrowed from the paper of Bobok and Daskalescu. Let G be a finite group, M a tuple of positive integers, IS the set of numbers from 1 to S, and let gamma MG be the set of maps from IS times G from Z to Z, such that AIG is greater than or equal to 0 for every IG in the domain. And this sum here where of the AIG, where I is fixed and G varies in the group, is MI for every I. And for any such map A and element H of the group, we can define a new map H times A such that H times A applied to IG is A applied to I GH, and this map also lies in gamma MG, and therefore we obtain an action of G on gamma MG. And the result we get from the previous theorem with this notation is that we have a bijection between the set of isomorphism classes of elementary G gradings on UTM and the set of orbits of this G action on gamma MG. So we can count the number of isomorphism classes of elementary gradings on UTM by using the well-known Burnside-Cauchy-Frobenius lemma that says that if we have a finite group G acting on finite set X, then the number of orbits is equal to the average number of fixed points. So this is given by this formula here. So when we use this lemma, the result that we get, which is our main result, is the following. Here we need this notation. Phi G is the map that associates to T the number of elements of G of order T. And well, G and M are as before, the group and the tuple of positive integers. So the number EGM of isomorphism classes of elementary G gradings on UTM is given by this formula. EGM is equal to 1 over the order of G. The sum here over the divisors T of this number D here of this products. D is the greatest common divisor of M1 to MS and the exponent of G. In particular, if we S S to be 1, then we're talking about matrix algebras. So if the result we have is the following: M is a positive integer, EGM is the number of isomorphism classes of elementary G gradings on MMF, and EGM is given by this formula here, which is just a particular case of the previous result with S equals 1. So, and this is the formula that we get from matrix algebras in this case. And for particular cases of the group, we can give quite explicit formulas for the EGM. For example, if you take a finite group of prime exponent P in order P to N, then EGM is equal to this up here if P doesn't divide M, and this here if P does divide M. We can take, for example, G to be the cyclic group of order Pn also, and for instance, we write M as P to K times M prime, where P doesn't divide M prime. And the number of isomorphism classes in this case is 1 over Pn times this formula here. So we can give quite an explicit formula in this case. And we also get the following. Well, if you, in a certain sense, these numbers EGM for every M, the sequence of numbers when you vary the M, the sequence EGM determines the group G if it is abelian. So the result is the following. If G and H are finite abelian groups, and EGM is equal to EHM for every natural number M, then G is isomorphic to H. The result does not necessarily hold for non-abelian groups. And well, we can also say something, at least, about the number of isomorphism classes of G gradings on matrix algebras, of arbitrary gradings, not only elementary gradings. So let M be a positive integer, and let NGM denote the number of isomorphism classes of arbitrary G gradings on MMF. So if the field is algebraically closed and G is a finite abelian group, then the sequences NGM and EGM, they have the same asymptotic growth. So more precisely, NGM grows asymptotically as EGM, which grows asymptotically as 1 over the order of G factorial times M to the order of G minus 1. So, well, this is the results that I had to present. This is some of the bibliography I used, and well, thank you for your attention.
Oh, thank you very much for the talk. Are there any questions or remarks?
Yeah, I have.
Yes, please go ahead.
In the last theorem, can you go the last? Yeah. Do you think this is going to be true also for G non-abelian?
No, because of this.
I'm saying that the asymptotics are the same.
Oh, I don't know. I don't know.
No, I understand that.
Yeah.
I'm talking about asymptotics.
No. Yeah. Well, I think you'd have to have, because the key point here is that in counting, when you mix the elementary gradings and the division gradings, the number that plays the biggest role is the number of elementary gradings.
Right.
So I think it could be true in the case of non-abelian groups, but I don't know enough about the classification to give bounds on the number of isomorphism classes of the division gradings, for example, in the case that G is non-abelian.
There is the notion of central type groups. If you want to get that the twisted group algebra is a matrix algebra.
Mm-hmm.
So the groups has to have a square order, of course. And okay, I mean, they are very difficult to classify, but at least the last theorem, I think it's reasonable.
Okay, so thank you.
Well, if everything is determined by the elementary gradings, then it may be true for non-abelian groups as well. Potentially. So any other questions or comments to the speaker? Well, if not, then let's thank the speaker.
Yeah,
Somebody wanted to see us the references, right?
Yeah,
so
thank you. Thank you very much.
I think it's time to start the next talk. So the next speaker is Marin Genov from the Institute of Mathematics and Informatics of Bulgarian Academy of Sciences and University of Miami, Florida. And he will speak about functions holomorphic over algebras. Please.
Thank you. First of all, thanks to the organizers for this great conference. Today, I would like to tell you a little bit about what one could do with a certain class of algebras, especially what kind of analysis one could do with that. There is a nice German term, Funktionen theory, which I borrowed, which literally translates as function theory, but really refers specifically to the study of complex differential functions of one or sometimes several complex variables. Usage actually varies throughout history and literature. But in this talk, we're going to have this distinction between one and several variables kind of disappear. The starting question really is, well, looking at our definition of complex differentiability, can we replace the algebra of complex numbers by another finite dimensional commutative associative unit of algebra A? And so naively, one can just adopt the same definition. One can take an open subset of an algebra A, of such an algebra A, and look at functions from U to A and call them A-differentiable if the well-known limit exists when letting H approach 0 via the invertible elements of A. And that actually works because the group of units is dense in A, so we can actually approximate to 0. But if you're too worried about well, invertible elements and all that, you can employ an equivalent definition. You can use Frege differentiability and arrive at exactly the same notion. Both definitions are completely equivalent in the finite dimensional setting. One direction is immediate, the other direction of the equivalence takes a little bit of work, however. And talking about A-differentiability, we can also talk about A-homomorphicity, meaning A-differentiability in a neighborhood of each point in the domain. And so, taking the collection of such functions, we actually get a sheaf of A-algebras with distinguished derivation. But we actually want more. To get an honest, proper function theory, we really require it to be a one-variable theory in a certain sense, and we wanted to satisfy certain key elements of the classical complex analysis, like, for example, some form of generalized Cauchy-Riemann equations, generalized one-variable Cauchy-Maurer integral theorems, one-variable Cauchy integral formula, and some form of analyticity. And the end game is to construct analytic and geometric flavors of a functor from the category of finite dimensional commutative associated universal algebras, and a target category that somehow captures such function theory. Well, the analytic flavor would be, for example, some collection of Hardy spaces, for example, and a geometric flavor would be some collection of geometric analytic spaces of an algebra, whatever that means. So. And if time permits, I'll also say a little bit more about this functor, quote unquote. And when trying to construct such a theory, it turns out that the first two features, well, Cauchy-Riemann equations and the Cauchy integral theorem is easy to realize in a quite broad setting. But when we get to the Cauchy integral formula, we meet an obstacle. We need to be able to make sense of integrating algebra valued differential one forms of this type. And so there is an immediate topological obstruction here. The group of units has to be connected just for the integral to be well defined. And a neat little lemma tells us that the group of units is path connected if and only if the algebra carries a compatible complex structure. So from this point on, we're going to assume that our algebra is complex. And before we can understand the analysis involved, we need to know some basic properties, algebraic properties of such algebras. By virtue of finite dimensionality, such algebras are Artinian, and so they decompose into finite direct sums of Walker-Artinian algebras. And for the purposes of function theory, it really suffices to consider only Walker-Artinian algebras. And moreover, a Walker-Artinian algebra decomposes as a C vector space into a direct sum of C and its maximal ideal. And so we get two kinds of components here, a scalar part and a nilpotent part, X. Just because every element in the maximal ideal is nilpotent, and in fact, the maximal ideal itself is nilpotent. And inside this decomposition, we can also identify the group of units as the elements, as a subset of elements having non-zero scalar part. It turns out that such algebras are also triangulable, so they're isomorphic to upper triangular algebras of this form, where the main diagonal consists of the same entry. So if we think of the elements of A as operators, the scalar part is really the eigenvalue. This justifies the name, spectral part, but there's a little bit more to it. Projecting an element onto the spectral part
is actually epimorphism of algebras. In fact, it is a retraction with respect to the inclusion of C into the algebra. And so it all sits in this cute little commutative triangle that actually determines much of the interplay between the classical complex analysis of a single variable and a function theory over the algebra. And so let's dive in. If we fix complex basis for our algebra, we can define the structure tensor of the multiplication in the algebra. If we write our homomorphic mapping, so homomorphic in the traditional sense, into components with respect to these spaces, so we get each component as a function, as a homomorphic function of several complex variables. Of course, each component is going to satisfy the usual Schrödinger equations for each complex variable. But the A differentiability of the differential of f puts additional restrictions on the partial derivatives in terms of a linear system of partial differential equations of first order with constant coefficients, the coefficients actually being the structure constants of the algebra. Okay, moving on, talking about differentiability, it's also completely natural to look at integrability, so the dual side, because the derivative is actually a derivation in these algebras, so meaning that it does not change the codomain of the function. It actually makes sense to look for primitives. And to understand integrability, there is key lemma lying at the heart of the whole function theory, really, that tells us that if f is ahomorphic, then the associated a valued one differential one form is del closed and has also declosed. So applying Stokes, well, literally gives us absolutely nothing, 0, if we integrate over one boundaries. And what this means for integrability is that removing a ball from the domain does not break it at all. In stark contrast to the complex plane, where just removing a point, of course, changes the class of functions having global primitives there. This is, of course, a big difference to the complex plane, but it's not really surprising because, well, we know from Hartog's extension theorem that compact singularities of functions, of homomorphic functions of several complex variables are removable. The next key step is to understand what is the analog of an index of a one cycle in an algebra. And the definition that works is really the analytic definition, that means the integral. As long as this integral, of course, is well defined, it has to be, the denominator has to lie in the invertible elements, so when integrating over gamma. And with the help of the spectral retraction, we can actually compute this index somewhat. We can reduce it to the complex plane case. The spectral retraction is a projection, so it's a continuous, in fact, an open map. And that induces a homomorphism of one cycles into the complex plane, actually into sigma u, really, into that part. And then the index of one cycle is just the index in the complex plane of the spectral part of the one cycle around the eigenvalue of Z0, which is an integer because it is the winding number of in the complex plane of this cycle. And with the help of this, well, armed with this index, we can state the index version of Cauchy's integral formula for closed curves. Namely, if f is ahomorphic, then the expected formula holds. Where we have to be careful that the integral, of course, on the right-hand side has to be well defined. So this has to happen over the invertible elements. And this has two implications. The first one being that, well, the values of f over a curve determine f on an unbounded set. In the plane, a simple closed curve encloses a bounded domain, but we no longer have this notion in higher dimensions. The second implication is analyticity. If f is ahomorphic at 0, then it can be expanded as a convergent power series with coefficients in A. And we'll have a look at this ring shortly. But to finish off on analyticity, it actually makes sense to define the analytic radius or the radius of convergence in just the same way as we do in a complex plane, because of the following theorem that tells us about the convergence behavior of such power series. Well, the power series expansion of F turns out to be locally normally convergent on the spectral ball with radius r. So these are the elements in the algebra with spectral radius less than r, which is nothing else but the open disk with radius r times the affine space M, our maximal ideal. And in fact, the power series is actually divergent outside of the closure of the spectral ball. The proof from the complex plane does not translate really to this setting. Because the absolute value, well, we no longer have absolute values, we only have submultiplicative norms in our dimensions. Okay, so let's have a closer look at this ring. So standard commutative algebra tells us that the ring of formal power series is actually local because A is local. But this turns out to be the case for the convergent power series as well. And so we can, when we look at the ring of, when we look at analytic germs, it turns the ring of analytic germs is local. And so when we take an open subset U of the Euclidean space underlying our algebra, and when we equip it with a structure sheaf of homomorphic function of ahomorphic functions restricted to U, we actually get an honest locally ring space. So this is very geometric. And there is an open question here whether this ring of convergent power series is actually Noetherian. There's some evidence towards that. The ring of formal power series over A is Noetherian, and the ring of convergent power series over C is Noetherian. So I suspect this to be the case, but I don't have a complete proof of this yet. But analyticity is actually useful for to answer a really childish curiosity here at this point. So if you look at the definition of differentiability, and knowing that we have many more non-invertible elements in our algebra, not just zero, we can ask simply, well, why can't we let H go to some other non-invertible element through the invertible elements of A? Well, the group of units is still dense, of course, in the algebra. And it turns out that this limit actually exists. And not only does it exist, but it's crucial in proving a homological version of Cauchy's integral formula, which we state next. But before we state it, we need a small definition, really. If we look again at the spectral projection, well, as already mentioned, it induces a map of one cycles into the complex plane. And then we define the spectral homology to be really the quotient group of one cycles modulo the pre-image of one boundaries. So this means that a one cycle in the algebra is called spectrally non-homologous if its spectral part is a one boundary in the complex plane, well, in sigma u. Really. And armed with this definition, we can state the full homological version of Cauchy's integral formula over A. So if F is ahomorphic and gamma is a spectrally non-homologous one cycle, then the expected formula holds. And once again, we have to be careful, of course, that integral on the right-hand side is well defined. And in fact, we also get an honest bilinear pairing between the spectral homology and the ahomorphic functions here, like in the complex plane. And I would like to stress that the spectral homology is really the right partner the right partner in this bilinear pairing. Okay, and so we have established at this point the homological version of Cauchy's integral formula, and we can proceed like in the standard complex analysis, like in a classical complex analysis, to prove Laurent series expansion of functions and singularities, of ahomorphic functions and singularities, and we can also prove of amorphic functions and singularities, and we can also prove the residual theorem. I'm not going to talk about them. because the proof is really very similar. But I would like to take a closer look from algebraic perspective at the Laurent series. These rings. So it turns out that both rings, the ones of formal Laurent series with finite principal parts and of convergent Laurent series with finite principal parts, are local rings. And there is a new type of singular behavior in these rings. So it turns out that if we have an ameromorphic function f, it's quite possible that it has a pole of a non-removable pole, so an honest pole, and 1 over f also has a non-removable pole there, like this example tells us here. And so it behaves a little bit like an essential singularity from the plane, in that you cannot get rid of it by just inverting the function. But at the same time, it is a pole because the principal part is finite and non-trivial. And so this begs a question: if we can somehow characterize such functions, if you can somehow identify such behavior, if you can identify essential poles. And there is a partial answer to this. Even though the ring of formal Laurent series with finite principal parts is only a local ring, we do have an honest logarithmic evaluation of it. It's well defined, and it is just taking the index of the lowest invertible coefficient. So, and related to this is the degree of the Laurent degree of a Laurent series, which is just the index of the lowest non-zero coefficient. So we allow so in this case we do allow the element to be nilpotent. That's an important distinction here. And it is just like the degree of a polynomial, just in the opposite direction, really, because the principal parts are finite. Okay, and with this we actually can give a partial answer to the previous question. So if the degree is negative, meaning that if f has a non-trivial principal part, and if it is invertible as we want it, and if it lies in the valuation ring, so this is the important condition, if it lies in the valuation ring with respect to our valuation, then the degree of 1 over f is also going to be negative, meaning that 1 over f is going to have a non-trivial principal part, finite, of course. And the open case is actually when the valuation of f is strictly between the degree and 0. And this question is important not just for the sake of the algebra, but it has geometric relevance here. So when we want to go global, the simplest kind of spaces we want to look at are analogs of Riemann surfaces for the case of such an algebra. So we can just define a Riemann surface over A to be a connected 1 dimensional manifold with a bihomomorphic transition functions. But if you think about how the theory of Riemann surfaces functions, you really care about meromorphic functions over them. You care about counting poles and zeros and so on, and mostly poles. And if you have such an essential pole, it really messes with your counting. And so just in order to build the basic theory of such thing from the perspective of a one variable theory, you need to understand when such phenomenon occurs. There's actually an abundance of examples for such kind of spaces. A big chunk of such examples comes from tori. So if you have a full-rank lattice in our algebra, the quotient space is going to carry such an A-analytic structure just by pushing forward the obvious analytic structure along the covering line. And another big portion of examples comes from Baire restriction. So I will just illustrate this as an example, what Baire restriction is without giving precise definition. So what we do, we take a complex algebraic curve or variety, whatever your favorite one is, and we take an algebra, such an algebra, for example, the dual numbers, where epsilon square is 0, and we just put it in this equation, but we do not forget the base that we are over the base C. So we write it we can write in such coordinates, and we can solve on both sides to get a high-dimensional complex variety. In fact, this is also smooth. And in fact, this, even though this is high-dimensional, it is a curve over the dual numbers carrying such a dual analytic structure. And with this, I hope I managed to give you some taste of this theory and hopefully get you a little bit excited. Thank you.
Well, thank you for the nice talk. Are there any questions or comments?
Yes, I can make some questions.
Okay. You have a question here?
Over here. Yes. Do you expect any theorem like Picard, like near the essential pole? Well, that's the first one. And second, do you expect any like uniformization, like Riemann or Riemann mapping theory?
Well, Picard will be difficult. So understanding essential, at the moment, only looking at essential poles, but they are poles, they are no essential singularities. And understanding, I don't have clear idea of the essential singularities. I mean, it's clear you have to have an infinite principal part, so infinite trivial principal part for this. But I don't have a clear understanding of the behavior there. And the singularity is really not just a point. So if you look at 1 over z, it is a coset. It is an affine space. It is coset in the residual field, but this is an affine space. It's the point plus all nilpotent elements. So it's the point plus the whole maximal ideal. What actually happened? I don't know what happens actually with proper essential singularities. But I do expect that some form of Picard holds, some certainly modified version of Picard holds. And yes, I do believe that uniformization could work, some form of uniformization could work. That's actually one of the points to look at such geometric structures, and also to understand how maybe to look at Koch structure. So Koch theory, such things.
So any other questions, comments?
I would like to ask you a question.
Yes.
Is there an analogy in the direction, for example, if one considers the ring of all so-called holomorphic functions, or I think they're called integral in English, which are holomorphic on the complex plane.
Okay, and functions.
For this, I mean that this ring has interesting properties. For example, it is not Noetherian, but finitely generated yields are principal. And I think that the field of meromorphic functions also has some non-interesting properties. But concerning, for example, in this ring, there is a Weierstrass theorem, which says that certain points are realizable as zeros of the holomorphic functions. Is there some?
Yeah, you can do this. You can go. There's a bit of problem with. So when you want to, the first technical problem is that you no longer have an absolute value. This is really strong in the complex domain because it is multiplicative, and in high dimensions you only get submultiplicative norms. So it's not always clear that this inequality is in our favor when we want to do arguments in the limit. But I do expect something like this to hold. I mean, you can, for example, define elliptic functions and so on similar in this, and you get convergence stuff.
Yeah, because this particular theorem allows to
deduce these properties.
Yes, yes. Well, the problem is, of course, that division is here you have nilpotent elements that you have to care, and so even the general Weierstrass theorems, like for several complex variables, so they do not work here, which is why actually talking about materiality and so on is kind of difficult. And it's a good question, yeah. Yeah, but I do expect many properties to translate. I do.
Thank you.
So any other questions, comments? Maybe I have a quick question. Did you assume everywhere that the quotient of your algebra by the radical was one-dimensional?
Yes, it's Markov. The algebra, it's a big Markov algebra, so it has to be. So so all local algebras over the complex numbers, when you pick the quotient, then you get the field C.
Well, why can't you allow matrix algebra, full matrix algebra when you take?
You mean non-commutative?
Yes.
Well, there are lots of, that's a really good question. There are lots of problems with non-commutativity. Well, first of all, sorry, let me. Well, I don't know its problem. The definition, so neither differentiability nor this quotient actually give you something meaningful. You can do this definition, you can do it from the right or from the left, but the class of functions you get are only linear functions. So it's not interesting. This has been proven, I think, a few times actually. I know Boris Rosenfeld has a proof of this for the quaternions, for example, and so on. This is one of the problems with commutativity. And there is actually an alternative approach to extending such things to the non-commutative domain, and this is by looking at a certain form of the Riemann equations. And so what one could say is, so we want our function to satisfy such certain linear partial differential equations with constant coefficients. Okay, and we don't say anything about these constant coefficients at first, but we want to be able to compose such functions. Okay, so meaning that if two functions lie in the solution set, we want their composition to also be a solution. And then it turns out that this is equivalent to all these coefficients being the structure tensor of an associative algebra, not necessarily commutative.
Mm-hmm.
And so there is an ansatz there to do, but it's it's a tricky. The non-commutative case is tricky for many reasons.
Mm-hmm. I see. All right, thank you. Next talk is by Pedro Fagundes from the Institute of Mathematics, Statistics and Scientific Computing of the State University of Campinas, and he will speak about the Lvov-Kaplansky conjecture. Please.
Okay, thank you very much. Well, first of all, I would like to thank the organizers for such a nice conference. And now I would like to congratulate Professor Vesselin Drensky for the occasion of his anniversary. Well, I'm going to talk about the Lvov-Kaplansky conjecture. And actually, my focus will be on some variation of this conjecture. Okay. All algebras here will be associative. Okay, I'll be just working with associative algebras. And we denote by f of x the free associative algebra generated by a set of non-commutative variables x1, x2, and so on. And here we have our basic definition that will follow us up to the end of this talk, which is the image of a polynomial on some algebra, which is the following. If I have a polynomial in m variables with coefficients in a field f, and I have an f algebra A, then we define the image of this polynomial f on this algebra A, just as the set of evaluations of this polynomial f and the elements of the algebra A. Of course, in the first view, image of f is just a subset of A. So some examples, the two first ones are very understood, very classical for in PI theory, which is the definition of polynomial identity and central polynomials. They can be defined in terms of maids of polynomials. And a very celebrated result by a Japanese mathematician, Shoda, in 1936, states that every traceless matrix can be realized as a commutator of two other matrices. And actually this proves that the image of the commutator xy minus yx on the matrix algebra is exactly the traceless matrix subspace. This result was proved initially in fields of characteristic 0 and generalized by Albert and Muckenhout in 1957 over arbitrary fields. And we also can realize the full matrix algebra as images of multilinear polynomials on the matrix algebra. Of course, there are simpler ones, since we just can take, for example, polynomials of degree 1, non-zero polynomials of degree 1, then we have that its image on the matrix algebra will be the full matrix algebra, but we have other examples as well. For instance, this one given by Kurana and Lam 2012, where he studied, actually he didn't study the image of this polynomial. They were worried about a more general questions about commutators and generalized commutators on matrix rings. But as a consequence of several results in this paper, we have that the image of the generalized commutator xyz minus zyx on the matrix algebra is also the full matrix algebra. And here we can see that 0, the center of the matrix algebra, the traceless matrices, and also the full matrix algebra can be realized as images of multilinear polynomials on the matrix algebra. So some basic properties, these two ones are quite easy to check. Properties for images of multilinear polynomials on some algebra, which is that the image is closed on the scalar product and also on the conjugation by invertible elements of the algebra A. Another property which we are using in soon, which is that the linear span of the image of a multilinear polynomial is a Lie ideal of the algebra. It's not just a subspace, but it's a Lie ideal of the algebra A. So if one is interested in understand the linear span of images of multilinear polynomials in some algebra, one can ask, what about the Lie ideals of this algebra? And fortunately, this is well understood in the case of the matrix algebra. Save some conditions here on the field and on the size of the size of the matrix. But this is a very known result by Einstein in 1955, where he classified the Lie ideals of the matrix algebra. And the Lie ideals are those 4 that appeared as images of multilinear polynomials in the examples in the examples in the last frame. Okay. As a corollary, if a polynomial is multilinear, then the linear span of this the image of this multilinear polynomial on the matrix algebra must be one of these 4 options. Actually, this was also proved by Bresar and Klepp in a more general setting in this nice paper, where no assumption on the polynomial is needed. It doesn't need to be multilinear, and also they consider not just the matrix algebra, but any finite dimensional central simple algebra. And they got similar result in this case, and some assumptions in the algebra are provided from these assumptions, from this result by Einstein. Okay, and they also got that the image would be zero, the center, the subspace generated by commutators, and or the entire algebra. Okay, so one may ask, okay, what about the image of a multilinear polynomial, the matrix algebra, not just the linear exponent? And this is what the Lvov-Kaplan's conjecture is about. It asserts that, it says that the image of a multilinear polynomial on the matrix algebra will be a vector subspace of the matrix algebra. Okay, and equivalently, by those computations that we have done in last frame, we can restate the Lvov-Kaplan's conjecture in the following. The image will be one of those four options. So one may ask about some positive solutions in the direction of Lvov-Kaplan's conjecture. A first simple result is when we consider multilinear polynomials of low degree. Of course, degree 1 is very trivial. And when we consider multilinear polynomials of degree 2, it's trivial if we have in mind the Schroeder, Albert, and Mooking out result, which is the main step to classifying images of multilinear polynomials of degree 2 on the matrix algebra, which will be one of these three options. And this is the proof. It's quite simple, but we must have in mind the Schroeder result to conclude this proof. But when we consider multilinear polynomials of degree 3, this is a much more wider problem. And actually, one of the most complete results that we have in the direction of degree 3 multilinear polynomials is this one given by Dickham and Klepp in 2016, where they classify image of such polynomials on the matrix algebra with entries in the complex number field, provided we have an order of the matrices is even or less than 17. It's a computational result, but is one of the best ones we have about degree 3 multilinear polynomials. We have another result studying images of multilinear polynomials of degree 3 on the matrix algebra, but there is no complete classification. We have results about the behavior of the image, which it's about sufficient conditions on the size of the matrices such that the image will contain traceless matrices. But in the direction of Lvov-Kaplan's conjecture, for polynomials of degree 3, we have this result. And I couldn't give this talk without saying about one of the best results in the literature, which is the positive solution of Lvov-Kaplan's conjecture for 2x2 matrices with entries in a quadratically closed field. This is a result by Kanobelov, Malev, and Rowan in 2012. So Lvov-Kaplan's conjecture it's not an easy problem. Then we could try to ask the following: okay, what could we do if we consider subalgebras, some nice subalgebras of the matrix algebra, and trying to understand what is the image of multilinear polynomials on such subalgebras? Yesterday, Thiago Castilho de Mello gave a very nice talk in this case when he considered the upper triangular matrix subalgebra. Okay, and today I would like to discuss about another case, which is the case of strictly upper triangular matrix algebra. Okay, so just for establish some notation, I will denote by J the strictly upper triangular matrices, the set of strictly upper triangular matrices inspired by the Jacobson radical of UTN, and I will denote by J in the power M, the M power of J. So we want to study the image of a multilinear polynomial of degree m on J, on strictly upper triangular matrices, okay? And a first observation that we could do here is the following. We are multiplying triangular matrices with diagonal 0, just 0 in the main diagonal. So if we multiply m such matrices, we are moving up through the diagonals, adding zeros, right? So if I multiply m such matrices, I will obtain strictly upper triangular matrices, of course, but the first m diagonals are 0. So it's easy to see that the image of multilinear polynomial degree m on J will be contained in J to the power m. So the question is when inclusion holds, okay? And fortunately, that was the case when we are with a non-identity. We know that J satisfies the nilpotency identity, of course. And what we want to show here is that modulo this identity, in case we are not with this identity or consequences of this identity, any multilinear polynomial, the image of any multilinear polynomial on the strictly upper triangular matrix algebra will also contains J in the power m, modulo this identity. And in this way, we will have the equality of these two subsets, and then we'll have that the image will be a subspace. Actually, what we want to do is this theorem. In case we have a multilinear polynomial of degree m, the image of this polynomial on J will be J in the power m, if and only if we are not dealing with a multilinear polynomial identity of J. This holds for any field. There is no restriction on the base field F. And from now on, I would like to give a sketch of the proof of this theorem. And the proof runs as following. From now on, I'm assuming that I'm working modulo the nilpotency identity. So I want to show the reverse inclusion that I have said before. So I want to show that the image contains J in the power n. So given a matrix A in J in the power n, we want to write this matrix as an evaluation of F in some matrices of J. And the first step here is the following. We rewrite our matrix A as sum of its diagonals. So HAI is the ith diagonal of A, okay? And we want to show that each diagonal can be realized as the image of the multilinear polynomial F on BI, matrices BI, B2 up to BM, where B2 up to BM are fixed for all diagonals. We are just changing, changing the first variable, the first evaluation, okay? So how to compute, okay, first, before computing these matrices, this will be enough to give us that this matrix A is in the image of F, since we know that F is a multilinear polynomial, and in particular, it's linear in any variables, for example, in the first one. So we can write our matrix A as an image of F in, in some matrices of J. And this will be enough to get the reverse inclusion, okay? So the question is how to compute the matrices BI, B2, up to Bn. First of all, we will rewrite our polynomial F as the sum of polynomials Fj, where each Fj is the sum of all monomials where the variable x1 appears in a position J, okay? And we will do the following computation, a straightforward computation. We replace each variable x1, x2, up to xm by these matrices with commutative variables in the first diagonal above the main diagonal. Okay, key plus 1. And we compute F in such matrices. When we compute F in such matrices, we have this not very beautiful expression, beautiful matrix. Each entry is given by the sum of polynomials. This first sum of polynomials is given by the evaluation of F1 in x1, x2, and xm. And the following polynomials are given by the evaluations of F2, F3, and Fm polynomials on these matrices. Okay. So if I make equal those evaluations, this evaluation, to some general diagonal in the m+1 diagonal, I will obtain a nonlinear system. And if I am able to find some solution of this nonlinear system, it means that the first non-zero diagonal of J in the power m can be realized as the image of F in some matrices from J. And actually, we can find the solution of this nonlinear system. But how to do, how to find such solution? We can find in the following. Using this is a very technical lemma, I will not prove it here, but we can replace all the variables with super index 2 up to m, which will give us replacement of the variables x2 up to xm for elements in F, such that all this sum is non-zero for all key. And this sum is appearing in this evaluation of the polynomial F1 in the variables x1 up to xn, okay? But if we can make all the sum non-zero for some evaluation, then the previous nonlinear system can be turned to a linear system, which can be, which we can find some solution recursively in the variables in red color. And then we are done with the first non-zero diagonal of J in the power m. So that means that the first non-zero diagonal of J in the power m can be realized as an evaluation of F on some matrices in J. So the question is how to do in the next diagonal, how to do with the next diagonals. And the answer is the following. We just need to change the first variable, moving respectively through the diagonal. And we do the same computation as before, where we fixed the variables x2 and xm, and we just change the first one. The question here is that appears this another sum, but actually this is not another sum. This one is a particular case of the sums that appeared before. So the same replacement of x2 and xm by those matrices b2 and bm also will give us non-zero values for this sum. And again, we can realize the other diagonals solving recursively some linear system in these variables in red. So in this way, we can prove that H diagonal is an evaluation of F in these matrices BI, B2, and BM, and that is what we would like to do, because we can use the linearity of F in the first variable to get all the matrix A in J in the power m. So we have the reverse inclusion, and then we have the equality, since the other inclusion is trivial. Actually, a more general result can be proved with considering just small changes in the last computations, but I prefer present the last computations since they are too technical already, so it's better to be in exposition. But actually, the same computation as before with just small changes prove that the image of any multilinear polynomial f on some power of j is equal to j in a power m times k, where m is the degree of the polynomial, if and only if f is not a polynomial identity of j in a power key. It's the same computations, just small changes. This also holds for any field. And this is what I would like to do today. Here I have some references. Thank you for your attention.
Let's thank the speaker. And are there any questions or comments from the audience?
Speaker returned the reference. Could the speaker return back so that we can see the references again?
Yeah.
I'm sorry, I couldn't.
You just, yeah.
Sorry, my connection was lost for a moment. Can you hear me now?
Yes, I can. I can hear you, for example.
Okay. So I couldn't hear if there were any questions to the speaker. Well, if there are no questions, then we are done for today.